Welcome to Quiet Law YouTube channel. There are questions that stretch back to the beginning of time itself. Mysteries that whisper to us from the furthest reaches of space, from the depths of our oceans, and from within the very fabric of our own minds. Tonight, we invite you to drift through 100 of the most profound puzzles that science has yet to solve. These are not tales of the unknown meant to disturb your rest, but rather gentle invitations to wonder, to contemplate the beautiful strangeness of existence itself. As you settle in, allow yourself to float through these mysteries like a traveler moving through fog, each question a soft landmark in an endless landscape of curiosity. There is no urgency here, no need to grasp for answers. Simply let these enigmas wash over you, reminding you of how vast and wondrous our universe truly is, and how much remains to be discovered. We begin our journey in the cosmos, in the silent vastness between stars, where light takes millions of years to travel, and where the very nature of reality bends in ways we're only beginning to understand. Let us ascend together into the darkness, and find comfort in the beauty of what we do not yet know. On a warm August evening in 1977, a radio telescope in Ohio detected something extraordinary. For 72 seconds, a signal arrived from space so powerful, so unexpected, that the astronomer reviewing the data the next day circled it on the printout and wrote a single word in the margin. Wow! This signal, forever after known as the Wow signal, came from the direction of the constellation Sagittarius, and to this day, no one knows what caused it. The signal was narrow-band, exactly the kind of transmission that astronomers had theorized an alien civilization might use to announce its presence. It matched the frequency of hydrogen, the most abundant element in the universe, a frequency that some scientists believe would be the universal choice for interstellar communication. And then, as mysteriously as it appeared, it vanished. Despite decades of listening, despite turning our most powerful telescopes toward that same patch of sky, the signal has never repeated. Was it a message from another world? A natural phenomenon we don't yet understand? The question hangs in the darkness between stars, unanswered, a whisper from the cosmos that we heard only once. But the Wow signal is not alone in its mystery. In recent years, astronomers have detected something equally puzzling: fast radio bursts. These are flashes of radio waves that last only milliseconds, yet in that brief instant, they release as much energy as the sun produces in an entire day. They come from billions of light years away, from galaxies so distant that the light we see from them began its journey long before Earth existed. The first fast radio burst was discovered in 2007, hidden in old data, but since then, hundreds more have been detected. Most appear only once, a single flash across the universe, and then silence. But some repeat, pulsing at irregular intervals, as though following some rhythm we cannot yet decipher. What could produce such intense bursts of energy? Colliding neutron stars? Evaporating black holes? Or perhaps something stranger still, something we haven't imagined? The universe flashes its secrets at us, but speaks in a language we're only beginning to learn. Even more mysterious are the odd radio circles that astronomers began discovering in 2019. These are enormous rings of radio emission, so large that they dwarf entire galaxies. They appear as perfect circles in radio telescope images, yet when we look at the same regions with optical telescopes, we see nothing unusual, just ordinary galaxies sitting at the center of these vast, invisible halos. Each odd radio circle is about 1 million light-years across. To put that in perspective, if our entire Milky Way galaxy were the size of a coin, these circles would be the size of a swimming pool. What could create such enormous structures? Some scientists think they might be the remnants of supermassive explosions from the early universe, shockwaves that have traveled through space for billions of years. Others propose they could be the edges of enormous bubbles blown by black holes. But the truth is, we simply don't know. These ghostly rings hover in our data, challenging our understanding of what's possible. And then there are the cosmic rays, particles that strike Earth's atmosphere with energies that seem to defy the laws of physics as we understand them. Most cosmic rays are protons or atomic nuclei, accelerated to incredible speeds by violent events in space. But some cosmic rays, the ultra-high energy ones, arrive with energies so extreme that they shouldn't exist. The most energetic cosmic ray ever detected carried the energy of a well-thrown baseball, compressed into a single subatomic particle. Imagine all that energy in something billions of times smaller than a grain of sand. These particles are traveling so fast, so close to the speed of light, that they should be slowed down by interactions with the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. There's a theoretical limit, called the GZK cutoff, beyond which cosmic rays shouldn't be able to travel far. Yet we detect cosmic rays that exceed this limit. Where do they come from? What could possibly accelerate particles to such speeds? The universe bombards us with mysteries we can see and measure, but cannot explain. All of these cosmic puzzles lead us to perhaps the most haunting question of all. Where is everyone? This is the heart of the Fermi paradox, named after the physicist Enrico Fermi, who, during a casual lunch conversation in 1950, asked a simple question that has echoed through the decades. Where are they? The universe is approximately 13.8 billion years old. Our galaxy alone contains hundreds of billions of stars, and we now know that planets are common, perhaps even universal. Many of these planets orbit in the habitable zones of their stars, where liquid water could exist. Even if life is rare, the sheer number of opportunities suggests that intelligent civilizations should have arisen many times. Some of these civilizations would be millions or even billions of years older than ours. Given enough time, even traveling at a fraction of the speed of light, an advanced civilization could colonize the entire galaxy in just a few million years, a blink of an eye in cosmic terms. So where are they? Why haven't we detected their signals? Why don't we see evidence of their engineering projects, their spacecraft, their presence? The silence is deafening. Perhaps life is far rarer than we think. Perhaps intelligence is a fleeting thing, civilizations rising and falling before they can reach out across the stars. Or perhaps they are out there, watching, waiting, staying silent for reasons we cannot fathom. The paradox remains. The universe seems too vast and too old for us to be alone, yet we find ourselves in what appears to be a cosmic solitude. These questions about what we can see, or cannot see, in the universe lead us to an even deeper mystery. Most of the universe is invisible. When astronomers calculate the mass of galaxies based on the light they emit, the numbers don't add up. Galaxies rotate too fast. They should fly apart, their stars flung into intergalactic space by centrifugal force. Yet they hold together, as though gripped by an invisible hand. That invisible hand is what we call dark matter. It doesn't emit light, doesn't absorb light, doesn't interact with ordinary matter in any way we can detect, except through gravity. Yet it must exist, because without it, galaxies wouldn't form, wouldn't hold together, wouldn't look the way they do. We estimate that dark matter makes up about 85% of all matter in the universe. Everything we can see, all the stars and planets and nebulae, all the light and fire and beauty of the cosmos, is just a small fraction of what's actually out there. But what is dark matter made of? That's the mystery. It's not ordinary atoms, not protons and neutrons and electrons. Physicists have built enormous detectors deep underground, shielded from cosmic rays, waiting for the faint whisper of a dark matter particle passing through. So far, they've detected nothing. The universe's dominant form of matter remains invisible and silent, known only by its gravitational influence, a ghost that shapes the cosmos. And if dark matter is mysterious, dark energy is even more so. In 1998, astronomers discovered something that shocked the scientific world. The expansion of the universe is accelerating. This shouldn't be possible. Gravity should be slowing the expansion down, pulling everything back together. Instead, something is pushing outward, causing space itself to expand faster and faster. We call this mysterious force dark energy, and it makes up about 68% of the total energy of the universe. Some physicists have proposed exotic explanations, including hypothetical particles called chameleon particles that change their properties depending on their environment, allowing dark energy to hide from our experiments. But the truth is, we have no idea what dark energy is or why it exists. We've discovered that most of the universe is made of something we cannot see, cannot touch, and do not understand. Some scientists think the answer might lie in another hypothetical particle called the axion. Originally proposed to solve a different puzzle in physics, axions have become a leading candidate for dark matter. These particles, if they exist, would be incredibly light and incredibly numerous, filling space like an invisible fog. Experiments around the world are searching for axions, trying to detect their faint interactions with magnetic fields. So far, the search continues, another thread in the tapestry of cosmic mysteries. All of this leads to perhaps the most fundamental mystery of all. Why does the universe exist the way it does? In the first moments after the Big Bang, matter and antimatter should have been created in equal amounts. When matter and antimatter meet, they annihilate each other in a flash of energy. If the universe had been perfectly symmetrical, everything should have cancelled out, leaving nothing but light. But we exist. Somehow, there was slightly more matter than antimatter, about one extra matter particle for every billion matter-antimatter pairs. That tiny asymmetry is why galaxies exist, why stars shine, why you are here listening to these words. This puzzle is called the baryon asymmetry of the universe, and solving it means understanding what happened in the first fraction of a second after the Big Bang, when the laws of physics were tested under conditions we can barely imagine. That brings us to the moment of creation itself, to cosmic inflation. In the 1980s, physicists realized that the universe we see today, so smooth and uniform at large scales, could only exist if space itself underwent a period of exponential expansion in the first tiny fraction of a second after the Big Bang. In less than a trillionth of a second, the universe expanded from smaller than an atom to larger than a grapefruit, smoothing out any irregularities and setting the stage for everything that would follow. Inflation explains many features of our universe beautifully, but it raises profound questions. What caused inflation? What kind of energy field could drive such rapid expansion? And what happened before inflation began? Some versions of inflation theory suggest that our universe might be just one bubble in an infinite froth of universes, each with different properties, each with its own laws of physics. We may never know if this is true, but the questions lead us to the edge of what science can explore. One of the deepest mysteries arising from those first moments is the arrow of time itself. Why does time flow in only one direction? Why do we remember the past, but not the future? Why does a dropped glass shatter, but a shattered glass never spontaneously reassemble? The fundamental laws of physics are time-symmetric. The equations work equally well whether time runs forward or backward. Yet the universe clearly has a direction, an arrow that points from past to future, from order to disorder. This is connected to entropy, the tendency of systems to move toward greater randomness. But why was the entropy of the universe so low at the Big Bang? Why did the universe begin in such an ordered state? If it had started in a high entropy state, there would be no arrow of time, no history, no evolution, no life. The fact that time flows as it does may be the most fundamental mystery underlying all others. Even the constants of nature hold mysteries. The fine structure constant is a number that appears throughout physics, describing the strength of electromagnetic interactions. For decades, it was thought to be truly constant, unchanging throughout space and time. But some observations of distant quasars suggest that this constant might vary slightly in different parts of the universe, or at different times. If true, this would shake the foundations of physics, suggesting that the laws of nature themselves might not be as universal as we thought. Then there are magnetic monopoles, theoretical particles that should have been created in abundance during the Big Bang. Unlike ordinary magnets, which always have both north and south poles, a magnetic monopole would have only one pole, north or south, but not both. The equations of physics allow for their existence, and inflation theory predicts they should be out there somewhere. Yet despite decades of searching, no one has ever found one. Why are they so rare, or do they exist at all? Neutrinos add yet another layer to the cosmic puzzle. These ghostly particles are produced in nuclear reactions, in the cores of stars, in supernovae, in the Big Bang itself. Billions of neutrinos pass through your body every second, streaming up from the sun and down through the Earth without interacting. For decades, we thought neutrinos were massless, but experiments have proven they have a tiny mass. The problem is, we don't know what that mass is, or where it comes from. The mechanism that gives neutrinos mass appears to be different from the one that gives other particles mass, and understanding this difference could unlock new physics. Some physicists have even proposed the existence of sterile neutrinos, hypothetical particles that don't interact through any force except gravity. These would be even more ghostly than ordinary neutrinos, nearly impossible to detect, yet they could make up some or all of dark matter. A few experiments have reported hints of sterile neutrinos, but the evidence remains controversial, another tantalizing possibility hovering just beyond confirmation. The Higgs boson, discovered in 2012, was a triumph of physics, confirming how particles get mass. But it also created a new puzzle, the Higgs mass stability problem. Quantum mechanics suggests that the Higgs boson should be trillions of times heavier than it actually is. Virtual particles should constantly interact with the Higgs field, adding enormous amounts of energy to its mass. Yet the Higgs has a relatively modest mass. Why? The only way to explain this is if different contributions to the Higgs mass cancel out with incredible precision, fine-tuned to many decimal places. Such fine-tuning seems unnatural, suggesting we're missing something fundamental. This connects to what's called the hierarchy problem. The gravitational force is about 1 trillion times weaker than the electromagnetic force. Why such an enormous difference? Why is gravity so weak? Some theories propose extra dimensions of space, dimensions that we can't see because they're curled up at incredibly small scales, and gravity alone can leak into these extra dimensions, diluting its strength in our familiar 3 dimensions. But we have no direct evidence for extra dimensions, and the hierarchy problem remains unsolved. Another puzzle lurks in the strong nuclear force, the force that holds atomic nuclei together. This force should, according to our equations, violate a fundamental symmetry called CP symmetry, which relates particles to their mirror images and their antimatter counterparts. Yet when we measure the strong force, it respects this symmetry almost perfectly. Why? This is the strong CP problem, and the most popular solution involves, once again, the hypothetical axion particle. If axions exist, they could naturally explain why the strong force behaves the way it does. But until we detect axions, the mystery persists. Perhaps no puzzle in modern physics is more debated than the black hole information paradox. According to Einstein's general relativity, nothing that falls into a black hole can ever escape. The event horizon is a one-way boundary, yet quantum mechanics says that information cannot be destroyed. If you throw a book into a black hole, the information in that book, the arrangement of atoms, the words on pages, must somehow be preserved. But how, if nothing can escape? Stephen Hawking showed that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon, and over time, they evaporate. But this Hawking radiation appears to be random, carrying no information about what fell in. So where does the information go? Is it somehow encoded in the radiation in ways we don't understand? Is it released in the final moments when the black hole evaporates? Or does it remain trapped in some remnant? Decades after Hawking first formulated this paradox, physicists are still debating the answer. This paradox is intimately connected to the quantum measurement problem, one of the most profound mysteries in all of science. Quantum mechanics tells us that particles exist in a superposition of states until they are measured. An electron can be in multiple places at once. A photon can be polarized in multiple directions simultaneously. But when we make a measurement, the superposition collapses into a single definite state. What counts as a measurement? Does it require a conscious observer? Does the universe split into multiple branches, one for each possible outcome, as some interpretations suggest? Or is there something deeper going on, some mechanism we haven't discovered that determines when and how quantum superpositions collapse into classical reality? We use quantum mechanics every day. It's the foundation of modern technology, from computer chips to lasers to MRI machines. Yet we still don't truly understand what it means, what it tells us about the nature of reality itself. And so we float here, at the edge of understanding, surrounded by darkness both literal and metaphorical. The universe speaks to us in whispers and flashes, in gravitational tugs and quantum uncertainties. We have built telescopes that peer billions of years into the past, accelerators that recreate conditions from the first moments of creation. Yet we find ourselves humbled by how much remains unknown. These cosmic mysteries are not obstacles but invitations, reminding us that reality is far stranger and more beautiful than we imagined. As you drift deeper into rest, let these questions become like stars in the night sky, distant and calm, marking the boundaries of our knowledge and hinting at the vastness that lies beyond. We descend now from the deepest questions of cosmic structure to something more immediate, more tangible. Throughout history, things have arrived at Earth from the void beyond. Most are unremarkable: dust, ice, fragments of ancient asteroids following their endless orbits. But occasionally, something arrives that defies our expectations, that challenges what we thought we knew about the solar system and the objects that drift through it. And sometimes, here on Earth itself, phenomena occur that seem to exist in the space between the explainable and the impossible. On October 19, 2017, a telescope in Hawaii detected something unprecedented. An object was moving through our solar system, but it hadn't come from the sun. Its trajectory showed clearly that it had arrived from interstellar space, the first such visitor we had ever confirmed. The astronomers named it Oumuamua, a Hawaiian word meaning scout, or messenger from afar arriving first. Oumuamua was strange from the beginning. As telescopes tracked its tumbling motion through space, they realized it was elongated, shaped perhaps like a cigar or a pancake, somewhere between 400 and 800 meters long, but only about 40 meters wide. Nothing in our solar system looks quite like this. Its surface was reddish, darkened by millions of years of exposure to cosmic rays as it drifted through the galaxy. It was tumbling chaotically, rotating every 7 to 8 hours, and it was moving fast, too fast to have originated from our sun. But the real mystery emerged when astronomers analyzed its trajectory with precision. As Oumuamua swung around the sun and headed back out into interstellar space, it accelerated. Not much, just a tiny deviation from the path gravity alone would dictate, but enough to be measurable, enough to demand an explanation. When comets approach the sun, they too exhibit non-gravitational acceleration. Ice on their surfaces vaporizes in the heat, and the jets of gas push them slightly off course. But Oumuamua showed no signs of being a comet. No tail, no cloud of gas and dust, no evidence of water ice vaporizing. It appeared to be a bare rock, yet it was accelerating as though propelled by some invisible force. Scientists proposed various explanations. Perhaps it was covered in frozen hydrogen or nitrogen, exotic ices that would vaporize without creating visible tails. Perhaps it was a fragment of a planet torn apart by tidal forces near another star, its unusual shape the result of that violent origin. One astronomer, Avi Loeb from Harvard, suggested something more provocative. Perhaps Oumuamua was artificial, a light sail constructed by an alien civilization, pushed by the pressure of starlight itself. This hypothesis remains controversial, but it highlights just how strange this object truly is. We watched Oumuamua for only 11 days before it became too faint to observe. It's now heading out of the solar system, never to return, taking its secrets with it. But it left us with a profound realization. Interstellar space is full of objects like this, wandering between the stars, and occasionally one passes close enough for us to see. Then, in August 2019, we found another one. Amateur astronomer Gennady Borisov was observing the sky from Crimea when he spotted a new comet. Within days, calculations confirmed what the orbital data suggested. This object, designated 2I/Borisov, later renamed interstellar object 3I/Atlas in some catalogues, was also a visitor from beyond our solar system. Unlike Oumuamua, Borisov looked and behaved like a comet. It had a distinct tail, a cloud of gas and dust streaming behind it as sunlight vaporized ice from its surface. Spectroscopic observations revealed water vapor, cyanide, and other molecules familiar from comets born in our own solar system. In many ways, Borisov seemed normal, reassuringly ordinary. Yet even in its ordinariness, Borisov was revealing. It showed us that other star systems produce comets just like ours, that the chemistry of planet formation might be universal. But it also had peculiarities. Its gas production was higher than expected for a comet of its size, and some of its properties suggested it had formed in a very cold environment, perhaps in the outer reaches of another planetary system, then been ejected by gravitational interactions with a giant planet. Borisov spent a few months passing through our solar system, came closest to the Sun in December 2019, and then headed back out into the darkness. As with Oumuamua, we could only watch as it departed, carrying with it information about another star system, another corner of the galaxy we'll likely never visit. These interstellar visitors are newcomers to our catalogue of cosmic mysteries, but Earth has a long history of objects arriving from space, sometimes with dramatic consequences. On the morning of June 30th, 1908, something exploded over the remote forests of Siberia near the Tunguska River. The blast was enormous, equivalent to 10 to 15 megatons of TNT, roughly 1,000 times more powerful than the atomic bomb dropped on Hiroshima. The explosion flattened 80 million trees across more than 2,000 square kilometers. Witnesses, even those hundreds of kilometers away, reported seeing a fireball in the sky, feeling intense heat, and hearing thunderous sounds. One man, sitting on his porch about 60 kilometers from the blast, felt such a wave of heat that he thought his shirt was on fire. The pressure wave was recorded on seismographs and barographs around the world. Yet when researchers finally reached the site years later, they found no crater. The trees at ground zero were still standing, stripped of their branches but not knocked down, while all around them, trees were felled in a radial pattern pointing away from the center. This suggested an aerial explosion, something that burst in the atmosphere before reaching the ground. The most widely accepted explanation is that a small asteroid or comet, perhaps 60 meters across, entered Earth's atmosphere and exploded at an altitude of about 5 to 10 kilometers. The heat and pressure of atmospheric entry would have been tremendous, and at some point, the object simply disintegrated, releasing all its kinetic energy in a massive airburst. But without a crater or significant fragments, we can't be certain. Some alternative theories have suggested everything from black holes to antimatter to alien spacecraft, though none of these have any real evidence supporting them. What we do know is that the Tunguska event is a reminder of how vulnerable Earth is to cosmic impacts, and how mysterious these events can be when we don't witness them directly or find clear physical evidence. There's another strange phenomenon associated with meteors that scientists are only beginning to understand: electrophonic sounds. Throughout history, people witnessing bright meteors or fireballs have reported hearing hissing, crackling, or popping sounds at the exact moment the meteor is visible overhead. This shouldn't be possible. Sound travels much slower than light, so if a meteor is high in the atmosphere, any sounds it makes should arrive many seconds or even minutes after you see it, just as thunder follows lightning. Yet the reports are consistent and come from credible observers, including scientists. For a long time, these accounts were dismissed as psychological, the brain perhaps creating an auditory sensation to match a dramatic visual event. But research in recent decades has provided a physical explanation. Very bright meteors create electromagnetic waves, likely through the ionization of air molecules in their wake, or through their interaction with Earth's magnetic field. These electromagnetic waves travel at the speed of light and can cause nearby objects to vibrate, glasses frames, hair, leaves, even the tiny bones in the inner ear. These vibrations create sound waves that the observer hears instantaneously with the visual sighting. It's a rare and strange phenomenon, a reminder that meteors interact with our environment in subtle ways we're still discovering. Space itself seems to reach down and touch our spacecraft in mysterious ways. Since the 1990s, scientists have noticed something odd. When spacecraft perform flyby maneuvers around Earth, using the planet's gravity to change their trajectory or boost their speed, they sometimes end up moving slightly faster or slower than predicted. This is called the flyby anomaly. The effect is tiny, changes in velocity of just a few millimeters per second, but it's measurable and unexplained. Not all flybys show the anomaly, and there's no clear pattern to when it occurs. Scientists have checked everything: the spacecraft's trajectories, Earth's gravitational field, atmospheric drag, tidal effects, even the rotation of the Earth. None of these fully account for the discrepancies. Some researchers have proposed exotic explanations: dark matter concentrated around Earth, modifications to gravity at certain scales, or unknown properties of spacetime itself. More conservative explanations suggest subtle thermal effects on the spacecraft, or errors in how we model Earth's complex gravitational field. But decades after its discovery, the flyby anomaly remains unsolved, a whisper of something we're missing in our understanding of celestial mechanics. The Pioneer anomaly was similar, but even more persistent. The Pioneer 10 and Pioneer 11 spacecraft, launched in the early 1970s, were humanity's first emissaries to the outer solar system. Pioneer 10 flew past Jupiter in 1973, and Pioneer 11 visited both Jupiter and Saturn. After their encounters with the giant planets, both spacecraft continued outward, heading for interstellar space. As mission controllers tracked the Pioneers across the solar system, they noticed something subtle but definite. The spacecraft were slowing down more than they should. The effect was small, about 10 trillionths of a meter per second, but it was constant and unexplained. After ruling out measurement errors and known forces, scientists were left with a genuine mystery. For years, the Pioneer anomaly sparked speculation about new physics. Could it be dark matter? A modification to gravity? Some unknown force acting on objects at the edge of the solar system? The mystery persisted until the 2010s, when a team of researchers painstakingly analyzed the spacecraft's thermal properties. The Pioneers carried nuclear power sources that generated heat. That heat was radiated preferentially in certain directions due to the spacecraft's design. The pressure from that thermal radiation, photons carrying momentum away from the spacecraft, created a tiny force pushing back on the Pioneers. When the calculations were complete, accounting for every component of the spacecraft and how heat was distributed and radiated, the numbers matched perfectly. The anomaly was solved, not by exotic physics, but by careful attention to mundane details. Yet the decades of mystery remind us how easily we can be fooled, how something as simple as heat can masquerade as something profound. Here on Earth, mysteries persist that are no less puzzling for being closer to home. Ball lightning is one of the most enduring enigmas in atmospheric science. For centuries, people have reported seeing luminous spheres, typically the size of a grapefruit, floating through the air during thunderstorms. These glowing balls move slowly, sometimes passing through walls or windows, and they can last for seconds or even minutes before vanishing, sometimes silently, sometimes with a loud bang. Accounts describe ball lightning as being white, yellow, orange, red, or blue. Some witnesses say it moves against the wind, as though under intelligent control. Others report a smell like sulfur or ozone after the phenomenon disappears. In rare cases, ball lightning has allegedly passed through aircraft windows or appeared inside buildings, causing burns or starting fires. For most of scientific history, ball lightning was considered folklore, dismissed because it seemed to violate known physics and because there were no photographs or scientific measurements. But as reports accumulated, including accounts from trained scientists and pilots, the phenomenon became harder to ignore. In recent decades, A handful of photographs and videos have emerged, and a few laboratory experiments have produced short-lived luminous spheres that might be related to natural ball lightning. The problem is, we don't have a complete theory that explains all the observations. Various mechanisms have been proposed: vaporized silicon from lightning striking soil, electromagnetic fields creating plasma structures, chemical reactions involving atmospheric gases, even quantum effects in the air. Some of these theories can explain some features of ball lightning, but none explains everything. And without being able to study the phenomenon under controlled conditions, ball lightning remains one of nature's most elusive mysteries. Another mystery comes not as light, but as sound. Around the world, people report hearing mysterious booms, loud enough to rattle windows and set off car alarms, yet with no visible cause. These are called skyquakes. They sound like sonic booms from aircraft or distant explosions, but investigations reveal no military activity, no supersonic flights, no blasting or industrial work that could explain them. Skyquakes have been reported for centuries, long before aircraft existed. In different regions, they have different names: Barisal guns in Bangladesh, mist puffers in the Netherlands, or Minari in Japan. They often occur near coastlines, but not always. Some happen in clusters, multiple booms over several days, then silence for months or years. Scientists have proposed various explanations. Some skyquakes might be caused by small earthquakes, particularly shallow ones, or those occurring underwater, where the energy is transmitted efficiently into the air. Others might be caused by meteorites breaking up in the atmosphere, too small to create visible fireballs, but large enough to generate shock waves. Changes in atmospheric pressure, distant storms, or even methane gas erupting from the seafloor have all been suggested. But many skyquakes remain unexplained, occurring in conditions where none of these mechanisms seem to apply. They serve as reminders that even something as straightforward as a sound, something we can hear and record, can come from sources we don't fully understand. Related to skyquakes are persistent hums, low-frequency sounds that some people can hear, but others cannot. The most famous is the Taos hum, named after the small town in New Mexico, where it was first investigated in the early 1990s. Residents reported hearing a faint but persistent humming or rumbling sound, often described as similar to a distant diesel engine idling. The sound was more noticeable at night and indoors, and it caused headaches, dizziness, and sleep disturbances in some people who could hear it. Scientists from several institutions came to Taos and conducted thorough investigations. They interviewed residents, conducted acoustic surveys, measured electromagnetic fields, and checked for industrial sources of vibration. About 2% of the population could reliably detect a sound in the frequency range described, but the instruments couldn't find anything unusual in the acoustic or electromagnetic environment. No source for the Taos hum was ever identified. The phenomenon faded from prominence in the late 1990s, though some residents still report hearing it. Similar hums have been reported in other locations around the world, including Bristol in England, Bondi in Australia, and Windsor in Ontario. Each investigation finds the same pattern. A small percentage of the population hears something, but measurements reveal no obvious source. Various explanations have been proposed. Some scientists think the hum might be related to very low-frequency electromagnetic waves that certain people's auditory systems can somehow transduce into perceived sound. Others suggest it could be infrasound, frequencies below the normal range of human hearing, that still affects the body. Industrial sources, seismic activity, ocean waves interacting with the continental shelf, and even the global electric circuit have all been proposed as potential causes. The Outer Hebrides hum is another example, reported on the Isle of Lewis in Scotland. Residents describe a low throbbing sound that's loud enough to disturb sleep and cause vibration sensations. As with Taos, investigations have failed to pinpoint a source, though some researchers suspect it might be related to underwater acoustic phenomena, perhaps from naval activity or seismic sources in the North Atlantic. What makes these hums particularly mysterious is that they're genuinely perceived by some people, but not others, and instruments don't consistently detect them. This raises questions about the limits of human perception, about how we sense our environment, and about phenomena that might exist at the edge of detectability, affecting some individuals, but remaining invisible to conventional measurements. These mysteries, from interstellar visitors to unexplained sounds, connect the vastness of space with the immediacy of our own planet. They remind us that strangeness exists at every scale, that Earth is not isolated from the cosmos, but embedded within it, subject to visitors and influences we're only beginning to catalogue and understand. As objects pass through our solar system from unimaginable distances, as sounds echo without clear sources, we find ourselves in a universe that is far more active, far more surprising, than we sometimes remember in our daily lives. Let these mysteries wash over you gently. There is no urgency to solve them tonight, no need to grasp for certainty. They are simply here, woven into the fabric of existence, waiting patiently for the day when we might understand them better. For now, they serve as lullabies of the unknown, strange and soothing in equal measure. We return now to Earth itself, to the laboratory and the familiar. Yet even here, in substances we handle every day, in phenomena we can recreate at will, mysteries persist. Water, glass, ice, the flow of fluids, these common things harbor secrets that have puzzled scientists for generations. Sometimes the most profound mysteries are not found in distant galaxies, but in a glass of water, in the way crystals grow, in the dance of light and sound at scales almost too small to see. Consider a simple experiment. Take a flask of water and subject it to intense sound waves, ultrasound vibrations far beyond what the human ear can detect. As the sound waves pass through the liquid, they create regions of high and low pressure. In the low pressure regions, tiny bubbles form and then collapse violently as the pressure rises again. This is called cavitation, and it's a well understood phenomenon. But something extraordinary happens during that collapse. For a brief instant, shorter than a billionth of a second, the collapsing bubble emits a flash of light. This is sonoluminescence, literally sound into light. And despite nearly a century of study, we still don't fully understand how it works. The light comes from a bubble smaller than a millimeter across, yet the temperatures inside that bubble during collapse might reach thousands of degrees, perhaps as hot as the surface of the sun. Some experiments suggest even higher temperatures, tens of thousands of degrees, all concentrated in a space smaller than a grain of sand. The bubble collapses at speeds exceeding the speed of sound in water, creating a shock wave that focuses energy inward. But where exactly does the light come from? Is it thermal radiation, simply the glow of superheated gas? Or is something more exotic happening? Some physicists have proposed that the extreme conditions inside the collapsing bubble might create plasma, ionized gas, glowing like a miniature star. Others have suggested quantum effects, vacuum fluctuations, or even fusion reactions, though these more extreme ideas remain controversial. What makes sonoluminescence particularly mysterious is its stability. A single bubble can be trapped in a standing sound wave and made to collapse rhythmically, flashing once per cycle, thousands of times per second, with incredible regularity. This suggests a delicate balance of forces, a self-organizing system whose behavior emerges from complex interactions we can observe, but not fully predict. It's a reminder that even simple systems, water and sound, can produce phenomena that stretch our understanding. Moving from the laboratory to the observatory, we encounter another puzzle tied to gravity itself. In 1954, French physicist Maurice Allais was conducting experiments with a pendulum, measuring how it moved in response to Earth's rotation. On June 30th of that year, a solar eclipse was visible from his location in Paris. Allais decided to continue his measurements during the eclipse, not expecting anything unusual. What he observed surprised him. During the eclipse, the pendulum's motion changed. Its plane of oscillation, which should have rotated steadily due to Earth's rotation, showed an anomalous precession, as though gravity itself had shifted. Alais repeated the experiment during another eclipse in 1959 and reported similar results. This became known as the Alais effect, and it immediately sparked controversy. According to general relativity and Newtonian gravity, a solar eclipse shouldn't affect a pendulum. The moon blocking the sun's light doesn't change the gravitational forces acting on Earth, or on a pendulum swinging in a laboratory. Yet Alais's results were intriguing enough that other scientists attempted to replicate them. The results have been mixed. Some experiments during eclipses have reported anomalies, changes in pendulum behavior or in gravimeters, sensitive instruments that measure gravitational acceleration. Other experiments have found nothing unusual. The effect, if it exists at all, is subtle and inconsistent. Various explanations have been proposed. Perhaps the anomalies are due to thermal effects, air currents, or electromagnetic disturbances caused by changes in sunlight during an eclipse. The human factor cannot be discounted either. Experimenters who expect to see an effect might unconsciously introduce biases. Some physicists have proposed more exotic explanations involving modifications to gravity or tidal effects from the moon's gravitational shadow, but these remain speculative. The scientific consensus today is skeptical of the Alais effect, viewing it as likely an artifact of experimental conditions rather than a genuine gravitational phenomenon. Yet the mystery lingers because we can't definitively rule it out, and because the idea that eclipses might affect gravity, even slightly, is tantalizing enough to keep some researchers investigating. From gravity, we turn to something even more everyday: freezing water. Common sense tells us that hot water takes longer to freeze than cold water. After all, the hot water must first cool down to the temperature of the cold water before it can freeze. Yet there are persistent reports, going back to ancient times, that hot water sometimes freezes faster than cold water under identical conditions. This is the Mpemba effect, named after a Tanzanian student, Erasto Mpemba, who in the 1960s noticed that hot ice cream mix froze faster than cold mix when he was making ice cream in school. When he mentioned this to his teacher and a visiting physicist, Dr. Dennis Osborne, they were skeptical but agreed to test it. To their surprise, they confirmed the effect. The Mpemba effect has been reproduced in various experiments, but not reliably. Sometimes hot water freezes faster, sometimes it doesn't. The effect seems to depend on a complex interplay of factors: the initial temperatures, the container shape and material, dissolved gases in the water, convection currents, evaporation, and supercooling. Several mechanisms have been proposed. Hot water evaporates faster, reducing the volume that needs to freeze. Hot water might develop different convection patterns that help distribute cold more efficiently. Dissolved gases come out of solution more readily in hot water, and degassed water might freeze differently. Supercooling, when water remains liquid below its freezing point, might occur more readily in cold water, paradoxically delaying freezing. Despite all these ideas, there's no consensus on what causes the Mpemba effect, or even whether it's a single phenomenon or multiple effects that happen to produce the same result. It's humbling to realize that something as simple as freezing water can still puzzle scientists. Water, the most common liquid on Earth, continues to surprise us. Water's solid form, ice, holds mysteries of its own. We think of ice as straightforward, water molecules arranged in a crystalline lattice, but there are actually many different phases of ice, at least 18 distinct crystalline forms, each stable under different conditions of temperature and pressure. And beyond these crystalline forms, there's amorphous ice, ice with no regular crystal structure at all. Amorphous ice forms when water is cooled so rapidly that the molecules don't have time to arrange themselves into crystals. It can also form under high pressure. There are multiple types of amorphous ice: low-density amorphous ice, high-density amorphous ice, and very high-density amorphous ice, and the transitions between them are not fully understood. Scientists are particularly interested in amorphous ice because it might be the most common form of water in the universe. In the cold of interstellar space and in the outer solar system, water vapor that condenses onto dust grains freezes instantly into amorphous ice. Understanding its properties could help us understand comets, icy moons, and the chemistry that occurs in space. But amorphous ice is difficult to study. It exists only under specific conditions, and it tends to transform into crystalline ice when warmed or left alone for too long. The exact structure of amorphous ice at the molecular level, how the water molecules are arranged and how they interact, remains an active area of research. Some scientists think there might be a liquid-liquid phase transition in water, a point where supercooled water transforms from one type of liquid to another with different density and properties, and amorphous ice might hold clues to this transition. From the disorder of amorphous materials, we turn to an unexpected kind of order. For most of the 20th century, scientists believed that crystals came in specific symmetries. A crystal is a repeating pattern of atoms, and the laws of geometry dictate which patterns can tile space perfectly. Crystals could have two-fold, three-fold, four-fold, or six-fold rotational symmetry, but not five-fold. A five-fold symmetry cannot tile a plane without leaving gaps or overlaps. Then, in 1984, Israeli materials scientist Dan Shechtman was studying an aluminum-manganese alloy when he observed an electron diffraction pattern that showed five-fold symmetry. This should have been impossible. When he published his findings, many scientists were skeptical. Linus Pauling, one of the most respected chemists of the 20th century, famously declared, "There are no quasicrystals, only quasi-scientists." But Shechtman was right. The material he had discovered was a quasicrystal, an ordered structure that never repeats, similar to the patterns in Penrose tilings, mathematical arrangements that can fill a plane with five-fold symmetry by using two different shapes in a non-repeating pattern. Quasicrystals have since been found in other alloys, and even in nature, in a mineral found in a Russian meteorite. The stability of quasicrystals remains somewhat mysterious. They are ordered, their atoms arranged in precise mathematical patterns, but they don't have the periodic structure of normal crystals. Why do atoms choose to arrange themselves this way? What energetic advantage does a quasicrystal structure provide? In some cases, quasicrystals are more stable than the crystalline phases of the same material, but we don't fully understand why. Quasicrystals have unusual properties. They're often hard and brittle, with low friction and low thermal conductivity. They're being explored for applications in coatings, insulation, and even surgical instruments. But beyond their practical uses, quasicrystals challenge our understanding of what constitutes order and how matter organizes itself at the atomic level. Growth itself, the way structures emerge from simple beginnings, is full of mysteries. Watch a snowflake form, or look at the branches of a tree, the veins in a leaf, the patterns of frost on a window, and you'll see fractal structures, shapes that repeat at different scales, where each small part resembles the whole. Dendritic growth, the formation of branching tree-like structures, occurs in many contexts. Crystals growing from solution, frost forming on cold surfaces, electrical discharges spreading through insulating materials, even the formation of river networks and coral reefs. The term dendritic comes from the Greek word for tree, and these patterns are characterized by a main stem with side branches that themselves have smaller branches, often creating intricate, self-similar patterns. The mathematics of dendritic growth is complex. It emerges from an instability. A smooth boundary is unstable when growing into a supercooled or supersaturated medium. Small protrusions grow faster than flat regions, amplifying themselves and creating branches. But the details of how these branches form, how they space themselves, and how the patterns become so regular and beautiful, involve subtle interactions between diffusion, surface tension, crystal structure, and thermal or chemical gradients. Scientists can simulate dendritic growth on computers, and the results often match reality beautifully, producing digital snowflakes that look remarkably like real ones. Yet each snowflake is unique, shaped by the specific conditions it experienced as it fell through the atmosphere, the temperature and humidity at each moment of its formation. The emergence of such complexity, from simple physical laws, remains one of nature's most elegant demonstrations of self-organization. Related to dendritic growth is another instability that occurs in fluids. Imagine a viscous fluid, like honey or oil, trapped between two plates. If you push a less viscous fluid, like air or water, into this gap, forcing it to displace the thicker fluid, what happens? You might expect the boundary between the fluids to remain smooth, the invading fluid pushing evenly against the viscous one. But that's not what happens. Instead, the boundary becomes unstable. Fingers of the less viscous fluid protrude into the more viscous one, creating intricate, branching patterns. This is the Saffman-Taylor instability, named after the scientists who first analyzed it mathematically in 1958. You can see this instability in many contexts. Pour syrup slowly onto a plate, and you might notice fingers forming at the edges as air displaces the syrup. In industrial processes, in oil recovery, where water is injected into underground reservoirs to push out oil, in the flow of magma through rock, in biological systems where fluids move through porous tissues, the Saffman-Taylor instability appears. The patterns it creates are beautiful and complex, sometimes looking like ferns or frost crystals, other times like abstract art. The exact shape depends on many factors: the viscosity ratio between the fluids, the speed of injection, the properties of the confining space. Small random perturbations at the boundary get amplified, and the system self-organizes into these finger-like structures. What makes the Saffman-Taylor instability particularly interesting is that it's a pattern-forming process that's sensitive to initial conditions, but still produces recognizable structures. Two experiments starting with slightly different conditions will produce different detailed patterns, yet both will show the characteristic fingering. This is an example of deterministic chaos, where the system follows precise physical laws, but produces unpredictable, complex outcomes. This brings us to one of the deepest unsolved problems in physics: turbulence. Pour water from a faucet slowly, and it flows smoothly in a steady stream. Increase the flow, and at some point, the smooth flow breaks down. Eddies form, swirls and vortices at all scales. The flow becomes chaotic and unpredictable. This is turbulence, and despite centuries of study, we don't fully understand how or why it happens. The transition from smooth, laminar flow to turbulent flow is one of the great mysteries of physics. We can predict, roughly, when turbulence will onset based on a dimensionless number called the Reynolds number, which compares inertial forces to viscous forces in a fluid. But predicting the exact moment of transition, understanding precisely how the instability develops, and describing the resulting turbulent flow mathematically remain extraordinarily difficult. Turbulence is everywhere. It's in the air flowing over an airplane wing, in the blood flowing through your arteries, in the swirling clouds of Jupiter's atmosphere, in the roiling surface of the sun. Turbulent flows mix fluids efficiently, transport heat and momentum, and dissipate energy. Much of our weather is driven by turbulent processes in the atmosphere and oceans. The equations that describe fluid flow, the Navier-Stokes equations, have been known since the 19th century. We use them successfully to design aircraft and predict weather. Yet we can't solve them analytically for turbulent flows. We can't prove mathematically that solutions even exist under all conditions. In fact, this is one of the Millennium Prize problems, with $1 million reward for anyone who can prove that smooth solutions to the Navier-Stokes equations always exist or provide a counterexample. Turbulence is a problem of scale. In a turbulent flow, energy cascades from large eddies to smaller and smaller ones, down to scales where viscosity finally dissipates the energy as heat. This cascade involves an infinite range of scales, or at least a very large range, and capturing all of them in a mathematical description or a computer simulation is prohibitively difficult. There's a famous quote attributed to several physicists, including Werner Heisenberg, who supposedly said on his deathbed, "When I meet God, I am going to ask him two questions: why relativity? And why turbulence?" I really believe he will have an answer for the first. Whether or not Heisenberg actually said this, it captures the profound difficulty of the problem. Turbulence is classical physics, nothing quantum, nothing relativistic, yet it defeats our attempts at complete understanding. Even plasmas, the fourth state of matter, where gas is so hot that electrons are stripped from atoms, exhibit waves and instabilities we're still working to understand. Langmuir waves are oscillations that occur in plasmas, where electrons move collectively, creating waves of charge density. They're named after Irving Langmuir, who discovered them in the 1920s. In a plasma, electrons are mobile while the heavier ions remain relatively stationary. If you disturb the plasma, pushing some electrons slightly, they'll oscillate back and forth at a characteristic frequency determined by the plasma's density. These oscillations are Langmuir waves, and they play important roles in many contexts. In the solar wind, in fusion reactors, in the ionosphere, even in astrophysical phenomena like pulsars. But Langmuir waves interact with other waves in complex ways. They can merge, creating waves at different frequencies. They can interact with electromagnetic waves, converting energy between different forms. They can trap particles, accelerating them to high energies. The full range of behaviors that emerge when Langmuir waves are present is still an active area of research, particularly in the context of fusion energy, where controlling plasma instabilities is crucial to achieving sustained fusion reactions. And then there's glass, perhaps the most familiar of all mysterious substances. Glass is everywhere, in windows, bottles, smartphone screens, optical fibers. We've been making glass for thousands of years, yet we still don't fully understand what glass is at a fundamental level. Glass is an amorphous solid, meaning it lacks the regular crystal structure of materials like metals or salt. When you cool a liquid like molten silica, the molecules slow down. In a crystalline material, they would arrange themselves into an ordered lattice as they solidify. But if you cool the liquid fast enough, the molecules don't have time to organize. They become stuck in a disordered configuration, still arranged like a liquid, but too stiff to flow. This is glass. The mystery is the glass transition itself. As you cool a liquid, its viscosity increases smoothly. At some temperature, called the glass transition temperature, the viscosity becomes so high that the material behaves like a solid on human timescales, even though it's not crystalline. But is this transition truly a phase transition in the thermodynamic sense, like the transition from water to ice? Or is it just a practical definition, a point where the liquid becomes too viscous to flow on timescales we care about? Different glasses have different properties depending on their composition and how they were cooled. The same liquid cooled at different rates can produce glasses with different densities and stabilities. This suggests that glass is not a single well-defined state, but a family of states, all trapped in different local minima of the energy landscape. Some scientists think that if you could wait long enough, eons perhaps, glass would eventually crystallize, finding the true lowest energy configuration. Others argue that glass represents a genuine thermodynamic state, stable indefinitely. The debate continues, and the glass transition problem remains one of the deepest unsolved problems in condensed matter physics. These mysteries, from the flash of a collapsing bubble to the nature of turbulence, remind us that the familiar world is no less strange than the distant cosmos. The forces that shape our everyday experience, that determine how fluids flow and how crystals grow, that turn liquids into solids and create patterns from chaos. These forces are woven through with questions we're still learning to ask, let alone answer. As you settle deeper into rest, let these thoughts drift through your mind like patterns in frost, like eddies in a stream. There's beauty in not knowing, in recognizing that mystery surrounds us always, in substances as common as water and glass, in phenomena as ordinary as the flow of a river or the formation of ice. The universe does not withhold its secrets out of malice, but offers them gradually, inviting us to look closer, to wonder more deeply, to find enchantment in the everyday. We turn now from the mysteries of physics to the mysteries of time itself, to things that have endured far longer than seems possible, to knowledge that was lost or perhaps never understood. The past reaches toward us through objects and structures, through manuscripts we cannot read and monuments we cannot fully explain. through living things that have remained unchanged for millions of years, as though time itself forgot to touch them. In these remnants of antiquity, we find questions that may never be answered, stories whose endings have been lost to the centuries. In the archives of Yale University's Beinecke Rare Book and Manuscript Library sits one of the world's most mysterious books. It's called the Voynich Manuscript, named after Wilfrid Voynich, the book dealer who purchased it in 1912, though the manuscript itself is far older, likely created in the early 15th century in northern Italy. The book contains about 240 pages of vellum, covered in flowing handwritten text and elaborate illustrations. The problem is, no one can read it. The text is written in an unknown script, using an alphabet that doesn't match any known language. The letters are clear and consistent, written with confidence, suggesting that whoever created the manuscript knew exactly what they were writing. But the language, if it is a language, has defeated every attempt at translation. Cryptographers, linguists, computer scientists, and amateur code breakers have studied the manuscript for over a century, applying every technique from frequency analysis to artificial intelligence, and all have failed. The illustrations are equally perplexing. The manuscript appears to be divided into sections. One section shows botanical drawings, plants with strange flowers and roots, many of which don't correspond to any known species. Another section contains what look like astronomical or astrological diagrams, circular charts with suns and moons and stars. There's a biological section with drawings of nude women bathing in pools connected by elaborate systems of pipes. Another section shows what might be pharmaceutical recipes. The final section is filled with text and star-like patterns whose purpose is completely obscure. Several theories have been proposed. Perhaps it's an elaborate hoax, constructed to look mysterious, but containing no actual meaning. But if so, it's an extraordinarily consistent hoax. Statistical analysis of the text shows patterns similar to natural languages. Some characters appear frequently, others rarely, and they combine in ways that suggest grammatical structure. The manuscript also predates modern ideas about what fake ancient documents should look like, making it an unlikely forgery from the Renaissance period. Perhaps it's written in a cipher, a code meant to conceal information. But if so, it's unlike any cipher used during that era, and it's proven impossible to break. Perhaps it's a constructed language, an attempt by a scholar or mystic to create a new system of writing. Perhaps it's a lost natural language, spoken by some small community and never recorded elsewhere. Or perhaps it's the product of a mind we would today consider disturbed, an elaborate personal system of symbols and meanings comprehensible only to its creator. Radiocarbon dating places the vellum between 1404 and 1438. The pigments used in the illustrations are consistent with Renaissance materials. But beyond these facts, the Voynich manuscript keeps its secrets. It sits in its climate-controlled case, its pages filled with knowledge or nonsense or something in between. A book that has been looked at by countless eyes, but read by none. From a medieval mystery, we travel much further back in time, to ancient Egypt and the Great Pyramid of Giza. Built around 2560 BCE as a tomb for the pharaoh Khufu, the Great Pyramid is one of the most studied structures in human history. For over 4,000 years, people have explored its passages, measured its dimensions, and marveled at the precision of its construction. Yet in 2017, scientists discovered something that had been hidden all that time: a massive void inside the pyramid. The discovery was made using muon radiography, a technique that detects cosmic ray muons, high-energy particles that rain down from space and can pass through solid rock. By placing detectors inside the pyramid and measuring how many muons came through from different directions, scientists could effectively X-ray the pyramid's interior. The data revealed a space at least 30 meters long, with a cross-section similar to the pyramid's main gallery, located above that gallery, but previously unknown. This is extraordinary for several reasons. The Great Pyramid has been thoroughly explored. Its internal passages have been mapped, its chambers excavated, its blocks counted. The idea that a space large enough to hold a commercial airliner could have remained unknown challenges our assumption that we understand this monument. The void appears to have no obvious entrance, no connection to the known passages. What is its purpose? Some Egyptologists think it might be a structural feature, a weight-relieving chamber designed to prevent the gallery below from collapsing under the pyramid's mass. Similar chambers exist above the king's chamber. But the void's size and location have also sparked speculation about hidden chambers, sealed passages, or lost artifacts. The pharaoh's actual burial chamber might be elsewhere in the pyramid, still undiscovered despite millennia of searching. Ethics and preservation concerns make it difficult to investigate further. Drilling into the pyramid or excavating new passages risks damaging a World Heritage Site. So for now, the void remains inaccessible, its contents and purpose unknown, a reminder that even our most studied monuments can still surprise us. Mysteries persist not only in structures, but in practices, in things that humans did in the past whose meanings we can only guess at. In the highlands of Papua New Guinea, in villages among the Onga people, there exist mummies, unlike any others in the world. These are the fire mummies, human bodies preserved through a process involving smoke and fire that creates remarkably well-preserved remains. The practice was documented by outsiders only in the 20th century and had largely ceased by the 1950s due to missionary influence and changes in local culture. But the mummies themselves remain, some displayed in village shrines, others hidden in caves or kept by families. The preservation technique involved several stages. After death, the body would be cut open and internal organs removed. The body cavity would be filled with plant fibers. Then the body would be smoked over a fire for weeks or months, the heat and smoke drying the flesh and preventing decomposition. Some bodies were additionally coated with clay or ochre. The result is a mummy that's rigid, darkened, and remarkably preserved, with skin and features still recognizable. The dry highland climate of Papua New Guinea helps maintain the mummies once prepared. Some are believed to be several hundred years old. The purpose of this elaborate process is not entirely clear. The mummies were clearly objects of reverence, ancestors made present through preservation. They may have served roles in dispute resolution, their presence invoked during village conflicts. They may have been seen as protectors, guardians watching over the living. The practice connects to broader beliefs about ancestors, death, and the permeable boundary between the living and the dead. What makes the fire mummies particularly poignant is how recently this knowledge was still active. People alive today remember when the last fire mummies were created. Yet already, much of the specific knowledge, the rituals and meanings, has been lost or exists only in fragments. It's a reminder of how quickly cultural knowledge can fade, how practices sustained for generations can disappear in a single lifetime. From human mysteries, we turn to the natural world and its own enigmas. In 2013, researchers working in the Amazon rainforest of Peru began noticing strange structures on leaves and branches. Tiny silken fences or corrals, circular or rectangular, intricate and delicate, each about 2 centimeters across. At the center of each structure sat a single tiny tower, a spire rising from the middle of the enclosure. The researchers had no idea what created them. They collected specimens and waited to see what would emerge. What hatched was a spider, but the structures themselves remained mysterious. The silken fences appeared to serve no obvious purpose. They weren't webs for catching prey. They weren't egg sacs. The young spiders didn't seem to use them after hatching. The structures were dubbed silkhenges, after their resemblance to miniature Stonehenges, circles of posts with something significant at the center. Since that initial discovery, similar structures have been found in other locations in the Amazon and elsewhere in South America. But despite years of study, their function remains unclear. The leading hypothesis is that they protect the spider eggs, either from predators or from parasites. The fence might prevent small wasps or flies from reaching the center. Or it might create a microclimate, regulating humidity or temperature around the developing eggs. But this remains speculative. The species that creates silkhenges hasn't been definitively identified, though it's likely in the genus Cyclosa. Different structures show variations in design, suggesting possibly multiple species with similar behaviors, or perhaps the same species adapting to different conditions. The mystery is compounded by how rarely these structures are noticed. They're small, ephemeral, easily overlooked in the dense complexity of the rainforest. Silk hinges remind us that even now, in an age of satellites and databases, of genetic sequencing and global communication, the natural world still holds secrets. There are behaviors we've never witnessed, species we've never named, relationships between organisms that we haven't begun to understand. The Amazon, despite decades of research, remains in many ways unknown. Some mysteries involve not what we don't know, but what refuses to change. Scattered around the world are organisms called living fossils, creatures that have remained essentially unchanged for millions, or even hundreds of millions of years. They exist in the present but belong, in appearance and anatomy, to the distant past. The coelacanth is perhaps the most famous. This large fish, over a meter long with distinctive lobed fins and a unique tail, was known only from fossils dating back hundreds of millions of years. Scientists believed it went extinct along with the dinosaurs 66 million years ago. Then, in 1938, a living coelacanth was caught off the coast of South Africa. The discovery stunned the scientific world. Here was a creature thought lost to time, swimming in modern oceans. Since then, small populations of coelacanth have been found in deep waters off East Africa and Indonesia. They live at depths of 100 to 300 meters, in underwater caves and volcanic slopes. They're slow-moving, eating small fish and squid, and they give birth to live young after a gestation period of up to 5 years, among the longest of any vertebrate. But the real mystery is why the coelacanth hasn't changed. Evolution hasn't stopped acting on these fish. They've accumulated genetic changes over millions of years. Yet their body plan, their basic structure, has remained stable since the Devonian period, over 300 million years ago. What ecological niche do they occupy that allows such stasis? What selection pressures maintain their ancient form, while other lineages diversify and transform? Horseshoe crabs are another example. Despite their name, they're not true crabs, but belong to an ancient group more closely related to spiders and scorpions. They've existed for over 400 million years, predating the dinosaurs, surviving multiple mass extinctions. Their blue copper-based blood is used in modern medicine to detect bacterial contamination, a strange intersection of ancient biology and modern technology. The nautilus, a shelled cephalopod, has changed little in hundreds of millions of years. Sturgeon, ancient fish with rows of bony plates instead of scales, have been around for over 200 million years. The ginkgo tree, the only surviving species of a once widespread group, has leaves and reproductive structures essentially identical to fossils from the Jurassic period. Living fossils challenge simple narratives of evolution as constant change and progress. They demonstrate that in stable environments, or when a body plan is well suited to available niches, organisms can persist essentially unchanged for timescales that dwarf the entire history of human civilization. They're windows into the past, living links to extinct worlds, yet they're not relics. They're successful organisms, well adapted to their environments, survivors not through luck alone, but through the effectiveness of designs refined over eons. Among the strangest of these ancient survivors are tadpole shrimp, small crustaceans also called shield shrimp or triops. They look like miniature horseshoe crabs, with broad, shield-shaped shells and many pairs of legs. Fossils virtually identical to modern tadpole shrimp date back over 200 million years. But what makes them truly remarkable is their life cycle. Tadpole shrimp live in temporary pools, vernal pools that fill with rain and dry up seasonally. The adults live only a few weeks, growing rapidly, feeding voraciously, and producing eggs. When the pool dries up, the adults die, but the eggs remain. These eggs can survive for years, even decades, in dried mud, waiting for rain. When water returns, the eggs hatch within hours. The young shrimp grow rapidly, completing their entire life cycle before the pool dries again. This resurrection ecology allows tadpole shrimp to inhabit environments that would be deadly to most animals. But more remarkably, the eggs can remain viable for extraordinary lengths of time. There are reports of tadpole shrimp eggs hatching after 50, 70, even 100 years of dormancy. This raises profound questions. What biological mechanisms allow an egg to remain viable for so long? How does the embryo inside sense when conditions are right to hatch? And what does this extreme dormancy mean for the species' evolution? If eggs from different generations can all hatch at once when rain finally comes, then individuals separated by decades or centuries can suddenly exist together, mixing genes across time in ways that don't occur in most species. Tadpole shrimp have been used in research on aging and dormancy, on how organisms survive extreme conditions, on the limits of biological time. They suggest that life's relationship with time is more flexible than we often assume, that biological clocks can be paused and restarted, that generations can overlap in unexpected ways. Finally, we come to the bristlecone pines, trees that grow in the harsh, high-altitude environments of the American West. These are among the oldest individual organisms on Earth. The oldest known living bristlecone pine, a tree growing in the White Mountains of California, has been alive for over 4,800 years. It germinated before the Egyptian pyramids were built, before the Bronze Age, before writing was invented in most parts of the world. Bristlecone pines grow incredibly slowly in their harsh environment. The wood is dense, resinous, and resistant to decay. Even after parts of the tree die, the deadwood remains intact for thousands of years, preserving a record of climate and growing conditions. By studying the growth rings of living and dead bristlecone pines, scientists have constructed continuous climate records extending back over 10,000 years. But the mystery is how these trees live so long. Most organisms accumulate damage over time. DNA degrades, cellular repair mechanisms fail, tissues lose function. This is aging, and it eventually leads to death. Yet bristlecone pines seem to evade, or at least greatly delay these processes. They grow so slowly that damage accumulates slowly too. Their wood is so resistant to pathogens and decay that infections and injuries that would kill other trees are merely inconveniences. Some researchers think the secret lies in the tree's meristems, the growing tissues that produce new cells. In most organisms, stem cells gradually lose function over time. In bristlecone pines, the meristems appear to remain functional indefinitely, producing new healthy tissue year after year, century after century. The tree essentially renews itself constantly, replacing old parts with new while maintaining continuity. But we don't fully understand the mechanisms. What genes are involved? What biochemical pathways allow such extreme longevity? Could insights from bristlecone pines teach us something about aging in other organisms, including humans? These ancient trees stand in their remote mountain groves, silent witnesses to millennia of human history, holders of secrets about time and survival that we're only beginning to decode. These mysteries of the past and of endurance remind us that time is layered, that the present moment contains echoes of deep history, of lost knowledge and persistent forms. As you drift towards sleep, imagine yourself as one of these ancient beings. A tree counting centuries in rings of wood, a creature unchanged since the age of dinosaurs, a book whose pages hold words no one can read. There's comfort in continuity, in the knowledge that some things endure despite the passage of time, that mysteries can be beautiful even when unsolved, perhaps especially when unsolved. Let the weight of ages settle gently around you, not as a burden, but as a blanket, warm and heavy and reassuring, carrying you down into darkness and rest. We arrive now at the deepest mystery of all, life. What is it? How did it begin? Why does it take the forms it does? For all our scientific understanding, for all the detail we've accumulated about DNA and cells and evolution, the fundamental questions remain wrapped in uncertainty. Life persists in ways that seem impossible, transforms in ways that defy logic, and endures conditions that should destroy it. In the mechanisms of living things, we find miracles disguised as chemistry, wonder masquerading as biology. The greatest puzzle is also the oldest. How did life begin? For billion years ago, Earth was a young planet, its surface still cooling, its atmosphere nothing like the air we breathe today. There was no oxygen, no ozone layer, no protection from ultraviolet radiation. The oceans were hot, possibly acidic, filled with dissolved minerals from volcanic activity. And somewhere, somehow, in this hostile environment, chemistry became biology. Non-living matter organized itself into the first living cell. We know this happened. We exist as proof. But we don't know how. The gap between the most complex chemical reactions we can imagine and the simplest possible living cell is vast. Even the most primitive single-celled organisms alive today are astonishingly complex, with thousands of genes, elaborate metabolic pathways, and sophisticated mechanisms for reproduction and repair. Scientists have proposed many scenarios. Perhaps life began in shallow pools warmed by volcanic springs, where cycles of wetting and drying concentrated organic molecules and drove chemical reactions. Perhaps it started in deep-sea hydrothermal vents, where mineral-rich hot water pours out of cracks in the ocean floor, providing energy and chemical gradients that could power early metabolism. Perhaps organic molecules arrived from space on comets and meteorites, seeding Earth with the building blocks of life. The RNA world hypothesis suggests that before DNA and proteins, life was based on RNA, a molecule that can both store information like DNA and catalyze reactions like proteins. In this scenario, self-replicating RNA molecules gradually evolved more complex functions, eventually giving rise to DNA and the protein-based life we know today. Laboratory experiments have shown that RNA can indeed catalyze reactions and even replicate itself under certain conditions, lending support to this idea. But enormous gaps remain. How did the first self-replicating molecule arise? How did metabolism begin? The coordinated set of chemical reactions that extract energy and build structures. How did the genetic code emerge? The mapping between sequences of nucleotides and sequences of amino acids in proteins. This code is essentially universal to all life on Earth, suggesting it arose early and was then locked in place. But why this particular code? Why these 20 amino acids and not others? Perhaps most mysteriously, how did life become cellular? All life exists in cells, membrane-bound compartments that separate inside from outside, self from environment. This boundary is crucial. It allows concentration of molecules, maintenance of different chemical conditions inside and out, and evolution of complexity. But membranes themselves are complex, made of lipids that must be produced through elaborate metabolic pathways. Which came first, metabolism or membranes? How did early chemical systems transition from being open, dispersed through the environment, to being enclosed, individuated, alive? These questions lead to an even stranger mystery, the chirality of life. Many molecules can exist in two mirror image forms, called left-handed and right-handed, like your left and right hands. They have the same atoms connected in the same sequence, but their three-dimensional shapes are mirror images of each other. In most chemical reactions that produce these chiral molecules, both forms appear in equal amounts. But life is not symmetrical. All amino acids in living things are left-handed. All sugars in DNA and RNA are right-handed. This homochirality, the exclusive use of one chiral form, is universal to all life on Earth. It's also essential. Proteins and DNA would not work properly if they contained both left and right-handed building blocks. The molecules wouldn't fold correctly, wouldn't fit together right. Why did life choose left-handed amino acids and right-handed sugars? Was it random chance? And once the choice was made, it became fixed because switching would break everything? Or is there some subtle physical reason, some asymmetry in the universe itself that favored these forms? Some experiments suggest that circularly polarized light from space, or interactions involving the weak nuclear force, which is itself chiral, might create slight excesses of one form over the other. But we don't know for certain. The handedness of life remains one of its deepest mysteries. Once life exists, once we have cells with DNA and proteins, another mystery emerges. protein folding. Proteins are chains of amino acids, hundreds or thousands of units long, and their function depends entirely on how they fold into three-dimensional shapes. A protein's amino acid sequence determines how it will fold, but the relationship between sequence and structure is extraordinarily complex. In principle, a protein could fold into countless different shapes. For a chain of just 100 amino acids, the number of possible configurations is astronomical, far more than the number of atoms in the universe. Yet proteins fold correctly and quickly, typically in milliseconds to seconds. This is Levinthal's paradox. If a protein had to try all possible configurations to find the right one, it would take longer than the age of the universe. Yet proteins fold reliably and fast. The answer involves a folding landscape, a concept where the protein doesn't search randomly, but follows paths of decreasing energy, like water flowing downhill. Local structures form first, small stable regions that guide subsequent folding. Chaperone proteins in cells help prevent misfolding and aggregate formation. But we still can't predict from sequence alone exactly how most proteins will fold. This is one of the great unsolved problems in biology, essential for understanding disease, since many illnesses involve misfolded proteins, and crucial for designing new proteins with desired functions. Life's transformations are no less mysterious than its origins. Consider metamorphosis, the process by which a caterpillar becomes a butterfly. A caterpillar is an eating machine, crawling on many legs, consuming leaves, growing larger. When it's ready, it forms a chrysalis, and inside that protective shell, something extraordinary happens. The caterpillar's body largely dissolves. Most of its tissues break down into a nutritious soup. Groups of cells called imaginal discs, which have been dormant inside the caterpillar since it was an egg, now activate. These cells multiply and differentiate, forming adult structures. Wings, compound eyes, long legs, antennae, reproductive organs. Within days or weeks, a creature that could only crawl emerges able to fly. We understand much of the molecular biology of metamorphosis, the genes that activate, the hormones that control timing. But the process itself remains almost miraculous. How does the genetic program coordinate such radical transformation? The caterpillar and butterfly share the same DNA, yet they're structured completely differently, shaped for different modes of life. Some studies suggest that butterflies retain memories from their caterpillar stage, meaning that even as most neurons break down and reform, some continuity of information persists through metamorphosis. From transformation, we turn to regeneration. Cut a flatworm called a planarian into pieces, and each piece will grow into a complete new worm. Cut off a planarian's head, and it will grow a new one, complete with a functioning brain. Cut off its tail, and a new tail appears. Some planarians can be cut into dozens, or even hundreds of pieces, and each fragment will regenerate a whole organism. This seems impossible. How does each piece know what's missing? How does it rebuild precisely the structures that were lost? Planarians contain stem cells throughout their bodies, cells that can differentiate into any tissue type. When the worm is injured, these stem cells migrate to the wound and begin rebuilding. But they don't just produce a mass of tissue, they recreate the exact structures needed. A piece that lacks a head grows only a head, not a second tail. This requires a body plan, information distributed throughout the organism about what the whole should look like. Bioelectric signals, patterns of electrical potential across cell membranes, appear to play a crucial role. Cells communicate through these electrical gradients, creating a kind of map that guides regeneration. Researchers can manipulate these signals and cause planarians to grow heads with different shapes, or even heads that resemble those of other flatworm species, suggesting the bioelectric pattern encodes structural information that's separate from the genetic sequence. Similar mysteries appear in axolotls, the Mexican salamanders that remain in an aquatic larval form throughout life. Axolotls can regenerate not just tails but entire limbs, complete with bones, muscles, nerves, and skin, all perfectly organized and functional. Cut off an axolotl's leg, and within weeks, a new leg grows back, indistinguishable from the original. This regeneration happens through a structure called a blastema, a mass of undifferentiated cells that forms at the wound site. Cells near the injury dedifferentiate, losing their specialized identities and becoming more stem cell-like. They then multiply and redifferentiate, forming all the tissues of the new limb in the correct positions. The limb grows in stages, forming first the upper portion, then the lower, then the digits, recreating the original structure with remarkable fidelity. Humans and most mammals cannot do this. We can heal wounds, regenerate liver tissue, and regrow fingertips in early childhood, but we cannot regenerate entire limbs. We have the same basic genetic toolkit as axolotls, yet we've lost or suppressed the regenerative program. Understanding what axolotls do differently could someday help us unlock regenerative capabilities in humans. But for now, their abilities remain beyond our reach, a reminder that evolution sometimes discards capacities that seem purely beneficial. Perhaps the most extreme example of regeneration involves not regrowing parts, but reversing time itself. Turritopsis dohrnii, sometimes called the immortal jellyfish, has a life cycle that defies normal aging. Like other jellyfish, it begins as a larva that settles on the seafloor and becomes a polyp, a stationary form that buds off swimming medusae, the familiar bell-shaped jellyfish. The medusae mature, reproduce, and normally die. But Turritopsis can reverse this process. When stressed by injury, starvation, or temperature change, or even spontaneously as part of its life cycle, an adult medusa can revert to the polyp stage. Its cells transdifferentiate, changing from one specialized type to another, and its body reorganizes into the earlier form. The polyp can then produce new medusae, effectively resetting the cycle. In theory, this process could continue indefinitely, making the jellyfish biologically immortal. Individual Turritopsis do die from predation, disease, or environmental hazards, but aging itself doesn't appear to limit their lifespan. They demonstrate that the arrow of development, from embryo to adult, is not as irreversible as we might think. With the right signals, cells can be reprogrammed, bodies restructured, time's direction reversed, at least biologically. Life's resilience extends even to death's door and beyond. Wood frogs, small amphibians found across North America, survive winter in a way that seems impossible. As temperatures drop below freezing, wood frogs stop breathing. Their hearts stop beating. Ice crystals form in their body cavities, in spaces between cells and organs. By any reasonable definition, the frog is frozen solid. Yet when spring arrives and temperatures rise, the frogs thaw and hop away, apparently unharmed. They accomplish this through a process called cryoprotection. Before freezing, the frog's liver converts glycogen to glucose, flooding the bloodstream with sugar. This glucose enters cells and acts as antifreeze, lowering the freezing point of intracellular fluid. Ice forms outside cells, but not inside them, preventing the sharp ice crystals that would puncture cell membranes and cause irreparable damage. The frog's metabolism doesn't stop completely during freezing. At the cellular level, some processes continue at extremely slow rates. Mitochondria, the cell's power plants, remain functional enough to prevent total energy depletion. When thawing begins, the heart restarts before breathing resumes, pumping glucose-rich blood to tissues to jumpstart metabolism. Still, the frog spends weeks or months in a state we would call dead. There's no heartbeat, no blood flow, no brain activity as we normally measure it. Yet the frog survives. This raises profound questions about the nature of death and the minimum requirements for life. If an organism can have no detectable vital signs for months and then resume normal function, what does it mean to be alive? For extremes of survival, few creatures match tardigrades, microscopic animals also called water bears. Tardigrades live in diverse environments, from mountaintops to ocean trenches, from tropical rainforests to Antarctic ice. They're most common in mosses and lichens, where they feed on plant cells or smaller organisms. They look like eight-legged bears under a microscope, plump and slow-moving, rarely more than a millimeter long. What makes tardigrades remarkable is their ability to survive conditions that would annihilate most life. When their environment dries out, tardigrades enter a state called cryptobiosis, essentially suspended animation. They retract their legs, expel most of their body water, and form a structure called a ton. In this state, their metabolism drops to less than 1/10,000th of normal levels. Tardigrades in cryptobiosis can survive extreme temperatures, near absolute zero and above boiling. They can withstand pressure 6 times greater than the deepest ocean. They've been exposed to the vacuum of space, to solar radiation far more intense than anything on Earth's surface, and to radiation levels thousands of times higher than would kill a human. After rehydration, they resume normal activity as though nothing happened. How do they survive? Part of the answer involves unique proteins that protect cellular structures during desiccation. When water leaves the cells, these proteins form a glass-like matrix that preserves the shapes of proteins and membranes, preventing damage from the stress of dehydration. Other proteins protect DNA from radiation damage, but we don't fully understand all the mechanisms. Tardigrades have genes found in no other animals, possibly acquired from bacteria through horizontal gene transfer, and these genes may contribute to their extreme resilience. Tardigrades force us to reconsider the limits of life. They demonstrate that living things can tolerate extremes we once thought impossible, that organisms can effectively pause their biology and restart it later. This has implications for astrobiology, for thinking about where life might exist in the universe. If tardigrades can survive conditions as harsh as outer space, perhaps life is more robust than we imagined, more likely to arise and persist in environments we consider hostile. Cancer is one of life's great threats. As we age, cells accumulate mutations. Some of these mutations disable the controls that regulate cell division. The result is cancer, cells dividing uncontrollably, forming tumors, spreading through the body. Cancer is common in long-lived animals, including humans. Yet naked mole rats, small rodents that live in underground colonies in East Africa, almost never get cancer. Naked mole rats are strange creatures. They're nearly hairless, with wrinkled skin and prominent teeth. They live in eusocial colonies like bees or ants, with a single breeding queen and many non-reproductive workers. They can live over 30 years, an extraordinary lifespan for a rodent. Mice, similar in size, typically live only 2 or 3 years and commonly develop cancer. Naked mole rats live 10 times longer and remain cancer-free. Research has revealed several mechanisms. Naked mole rat cells produce high levels of a molecule called high molecular weight hyaluronan, a component of connective tissue. This molecule appears to trigger a particularly strong contact inhibition response, causing cells to stop dividing when they touch each other. In most mammals, cells divide until they're closely packed. In naked mole rats, they stop dividing at lower densities, preventing the formation of tumors. Their cells also have unusually robust DNA repair mechanisms and more sensitive tumor suppressor genes that cause damaged cells to self-destruct before they become cancerous. But exactly why naked mole rats evolved these mechanisms while other rodents didn't remains unclear. Their long lifespan might be related. Longer lives mean more time for cancer to develop, so stronger cancer resistance would be advantageous. But this doesn't fully explain their extraordinary resilience. Naked mole rats have another trick. They can survive without oxygen for up to 18 minutes. When deprived of oxygen, most mammals die within minutes as brain cells run out of energy and perish. Naked mole rats switch to a different metabolic pathway, using fructose instead of glucose as fuel. This allows their cells, particularly brain and heart cells, to continue producing energy even without oxygen. This ability likely evolved because naked mole rats live in underground tunnels with poor ventilation. Oxygen levels in their burrows can drop significantly, and the ability to survive temporary oxygen deprivation would be advantageous. But the mechanism, metabolic flexibility, that allows switching between fuel sources, is unique among mammals and suggests that mammalian metabolism is more plastic than we realized. One more mystery of regeneration and survival bdelloid rotifers. These are microscopic aquatic animals, smaller than most single-celled organisms. They've been around for millions of years, but there's something extraordinary about them. No male bdelloid rotifers have ever been found. The entire group reproduces asexually, females producing daughters genetically identical to themselves. This should be evolutionarily disastrous. Sexual reproduction, the mixing of genes from two parents, creates genetic diversity that helps species adapt to changing environments and resist diseases. Without sex, harmful mutations should accumulate over time, a process called Muller's ratchet. Yet bdelloid rotifers have persisted for tens of millions of years without sex, apparently thriving. How? They have several tricks. They frequently exchange genes with bacteria and other organisms through horizontal gene transfer, acquiring new genetic material without sexual reproduction. They also undergo frequent desiccation, drying out completely and then rehydrating. This process breaks their DNA into fragments, and when the DNA is repaired during rehydration, pieces sometimes get rearranged, creating new genetic combinations. It's a form of genetic mixing that doesn't require sex. Bdelloid rotifers also appear to have highly efficient DNA repair mechanisms and may have ways of purging harmful mutations more effectively than other organisms. They're nearly immortal in another sense too. Individuals can survive desiccation for years and then resume active life, effectively pausing their biological clocks. Finally, a mystery from the ocean's deep: the squid beak. Squids are soft-bodied animals with no bones or shells. Yet they have a hard, sharp beak used to tear apart prey, made of a material similar to fingernails or bird beaks, but far tougher. The beak of a giant squid is strong enough to cut through steel cable. The mystery is the transition. The beak attaches directly to soft muscle tissue. Hard materials and soft tissues have very different mechanical properties. When you try to attach them together, stress concentrates at the interface, and the materials tend to tear apart. It's like trying to glue a steel rod to rubber. The junction is a weak point. Squid beaks solve this problem through a gradient. The tip of the beak is extremely hard, containing high concentrations of protein polymers that cross-link into a rigid structure. Moving toward the base, the material gradually becomes softer and more flexible, matching the stiffness of the surrounding tissue. This gradient spans several orders of magnitude in stiffness over just a few millimeters. How squids produce this gradient, how they control the cross-linking of proteins so precisely, remains incompletely understood. Engineers and materials scientists study squid beaks for insights into designing synthetic materials that can interface hard and soft components without stress concentration. It's an example of biological engineering that surpasses our current technology, a solution to a materials problem that nature discovered long before humans existed. These mysteries of life, from its origin to its persistence, from its transformations to its resilience, remind us that living things are not just complicated chemical reactions. They're systems of systems, processes folded within processes, matter organized in ways that create something genuinely new. Autonomy, purpose, the capacity to maintain themselves against entropy, to heal, to adapt, to endure. Life is chemistry, but it's chemistry that has learned to preserve and perpetuate itself, to resist dissolution, to assert its presence against a universe that tends toward disorder. As you rest now, think of your own cells, trillions of them, each one a descendant of that first living cell billions of years ago, each one carrying forward the improbable project of existence. Your body repairs itself while you sleep, proteins folding, DNA replicating, cells dividing and dying and being replaced, all without conscious effort, all following programs refined over eons. You are a mystery made of mysteries, a temporary arrangement of matter that somehow knows itself, that can wonder about its own nature. Let that thought comfort you as you drift deeper. You are improbable and precious, a continuation of something that began in ancient seas and has never stopped, life passing through you as it has passed through countless beings before and will through countless beings after. An unbroken chain of existence, stretching back to the very beginning and forward into an unknowable future. We turn now from the individual to the collective, from single organisms to groups that behave as unified wholes. In nature, some of the most sophisticated behaviors emerge not from individual intelligence, but from simple rules followed by many. Insects that barely have brains create structures of architectural perfection. Bacteria coordinate their actions across millions of individuals. Creatures navigate across continents using senses we're only beginning to understand. These are nature's algorithms, solutions to complex problems that arise from simplicity repeated, from local interactions that produce global patterns. Inside a beehive, in the darkness, worker bees construct honeycombs with extraordinary precision. Each cell in the comb is a hexagon, six-sided, and these hexagons tile together perfectly with no gaps or overlaps. The walls meet at angles of exactly 120 degrees. The cells are oriented slightly upward, tilted about 13 degrees from horizontal, just enough to prevent honey from flowing out. The consistency is remarkable. Honeycombs built by different colonies, different species of bees, in different parts of the world all show the same hexagonal pattern. Why hexagons? Mathematically, there are only three regular shapes that can tile a plane perfectly: triangles, squares, and hexagons. Of these three, hexagons enclose the most space with the least perimeter. This is important because bees build their combs from wax, which they must produce from their own bodies. Producing wax is metabolically expensive. A bee must consume about 8 kilograms of honey to produce 1 kilogram of wax. So efficiency matters. Hexagons allow bees to store the maximum amount of honey while using the minimum amount of wax. But how do bees create such perfect hexagons? They have tiny brains, no blueprints, no rulers or compasses. Each bee works independently, yet the collective result is geometrically precise. For a long time, scientists believed bees must somehow measure and construct hexagons deliberately, using their bodies or antennae as templates. More recent research suggests a simpler explanation. Bees initially build circular cells, working from instinct to create roughly cylindrical chambers. The wax is warm and soft when first secreted. As bees build more cells close together, the walls of adjacent circles press against each other. Surface tension and the physical properties of the wax cause these walls to flatten and meet at angles, and the most stable configuration is three walls meeting at 120-degree angles. The hexagonal pattern emerges naturally from the physics of closely packed circles. The bees then refine the structure, chewing and reshaping the wax, but the basic hexagonal tessellation arises from simple physical principles rather than complex cognitive planning. It's an example of stigmergy, a mechanism where the structure being built guides the building process. The bees respond to what's already there, and the geometry emerges from their collective, uncoordinated actions. Similar collective intelligence appears in ant colonies. An individual ant has a brain smaller than a pinhead, with perhaps 250,000 neurons compared to the 86 billion in a human brain. Yet ant colonies display behaviors that seem intelligent. They find the shortest paths between food sources and their nest. They allocate workers efficiently to different tasks. They adapt to changing conditions. They wage coordinated wars against rival colonies. One of the most studied behaviors is foraging optimization. When ants leave their nest searching for food, they wander somewhat randomly. When an ant finds food, it returns to the nest while laying down a chemical trail, a pheromone that other ants can detect. Ants leaving the nest tend to follow these pheromone trails. If a trail leads to food, more ants follow it, and each ant reinforces the trail with its own pheromone. If a trail leads nowhere, ants stop following it, and the pheromone evaporates. Over time, the colony converges on the most efficient routes. Shorter paths accumulate pheromone faster because ants can complete the round trip more quickly, reinforcing those paths more frequently. Longer paths or paths to depleted food sources fade. The result is ant colony optimization, an algorithm that has inspired computer scientists designing programs to solve routing and scheduling problems. No individual ant understands the colony's needs or plans the optimal route. Each ant follows simple rules. Lay pheromone when carrying food, follow strong pheromone trails, wander randomly when no trail is present. From these simple rules, complex colony-level behavior emerges. The colony as a whole appears to make decisions, but the decision is distributed across thousands or millions of individuals, none of whom grasp the larger pattern. Even bacteria, single-celled organisms with no nervous systems, can coordinate their behavior. Quorum sensing is a process by which bacteria detect how many of their kind are nearby and change their behavior accordingly. Bacteria continuously release signaling molecules into their environment. When bacterial density is low, these molecules diffuse away and their concentration remains low. But as bacteria multiply and become crowded, the concentration of signaling molecules increases. When the signal reaches a threshold concentration, indicating that a quorum has been reached, bacteria activate certain genes. These might be genes for producing light, as in bioluminescent bacteria that light up only when they're present in large numbers. They might be genes for producing toxins or for forming biofilms, protective communities of bacteria embedded in a matrix of proteins and sugars. They might be genes for virulence factors that help the bacteria invade a host. Quorum sensing allows bacteria to act collectively. A single bacterium producing toxins or light would waste energy for little benefit. But a million bacteria acting together can produce enough toxin to overwhelm a host's immune system or enough light to be visible. It's a form of communication and coordination that occurs at the chemical level, allowing populations to behave in ways that individuals cannot. The discovery of quorum sensing changed how we understand bacterial infections and biofilms. It revealed that bacteria are not solitary organisms acting independently, but social creatures that communicate and cooperate. This has led to research into disrupting quorum sensing as a way to fight bacterial infections, interfering with their ability to coordinate attacks on the immune system. In the rivers of South America, electric eels hunt in packs, and when they do, something remarkable happens. Each eel can generate electrical discharges of up to 800 volts, used to stun prey and defend against predators. When a group of eels encounters a school of fish, they begin to discharge in synchrony, their electrical pulses aligned within a few milliseconds of each other. This synchronized discharge is far more effective than individual eels shocking randomly. The combined electrical field is stronger and covers a larger area, stunning more prey. But how do the eels coordinate? They can detect each other's electrical fields through specialized electroreceptor organs. When one eel discharges, others sense it and time their discharges to align. It's a form of electrical communication and coordination that happens faster than nerve impulses could travel. The mechanism is still being studied, but it appears to involve a combination of sensory detection and phase locking, where oscillating systems synchronize their rhythms through mutual influence. This same principle explains how fireflies can synchronize their flashing, or how neurons in the brain can fire in coordinated patterns. The eels essentially entrain to each other's electrical rhythms, creating a collective behavior that emerges from individual responses to local signals. Bacteria demonstrate another form of collective navigation through magnetotaxis. Magnetotactic bacteria contain chains of magnetic crystals called magnetosomes inside their cells. These crystals, made of magnetite or graphite, act like tiny compass needles, aligning the bacteria with Earth's magnetic field. In the northern hemisphere, the bacteria swim downward along magnetic field lines. In the southern hemisphere, they swim upward. Why would bacteria want to follow magnetic fields? These bacteria live in aquatic sediments at the boundary between oxygenated water above and oxygen poor or anoxic sediments below. They need to maintain themselves at this boundary, where conditions are optimal for their metabolism. The magnetic field lines happen to point downward in the northern hemisphere and upward in the southern hemisphere, angling through the optimal zone. By following the field, bacteria can efficiently navigate to their preferred depth without having to sense oxygen concentrations directly. The formation of magnetosomes is itself a mystery. The bacteria must create these perfect magnetic crystals inside their cells, controlling their size, shape, and arrangement. The crystals are single magnetic domains, meaning each crystal acts as a single magnet, and they're arranged in chains so their magnetic moments add up. This is biological nanotechnology, the precise assembly of inorganic materials by living cells for a specific function. Magnetotactic bacteria were discovered only in 1975, and researchers are still uncovering details of how they use magnetotaxis. Some species appear to use a combination of magnetic and chemical sensing. The presence of magnetotactic bacteria in ancient rocks has even been proposed as a biosignature, evidence of past life that could potentially be detected on other planets. From bacteria, we turn to one of nature's great migrations. Every year, millions of monarch butterflies travel up to 3,000 miles from Canada and the United States to specific overwintering sites in the mountains of central Mexico. They're not following learned routes or migrating with experienced guides. The butterflies that make the journey south have never been to Mexico before. They're several generations removed from the butterflies that left Mexico the previous spring. Yet they navigate precisely to the same forests, even to the same trees, that their great-great-grandparents used. How? The butterflies use a time-compensated sun compass, meaning they can determine direction by the sun's position while accounting for the time of day and the sun's movement across the sky. This requires an internal clock and the ability to integrate celestial navigation with temporal information, a sophisticated computational task for an insect brain. But sun compass navigation alone can't explain the precision of their migration. Recent research suggests monarchs can also detect Earth's magnetic field, possibly using magnetic crystals in their antennae similar to those in magnetotactic bacteria. They may use a combination of solar, magnetic, and perhaps even chemical cues, the scent of the overwintering forests carried on the wind. The genetic and neurological basis of this navigation remains incompletely understood. Somehow, the instructions for a 3,000-mile journey to a specific location are encoded in the butterfly's nervous system, passed down through generations that never meet, each generation completing part of the journey. The butterflies that arrive in Mexico will overwinter there, then fly north in spring, laying eggs on milkweed plants. Their offspring will continue north, and it will be the 4th or 5th generation that makes the journey south again. Another mystery of timing is found in cicadas. Most cicadas have life cycles of 2 to 5 years, living as nymphs underground, feeding on tree roots before emerging as adults. But some North American cicadas have extraordinarily long and precisely timed cycles. Periodical cicadas emerge every 13 or 17 years, depending on the species. All members of a local population emerge in the same year, creating a massive synchronized event. When they emerge, they do so in enormous numbers, sometimes millions per acre. The air fills with their buzzing mating calls. They cover tree trunks and buildings. For a few weeks, they dominate the environment, mating and laying eggs. Then they die, and the forest falls quiet for another 13 or 17 years. Why such long cycles? And why prime numbers, 13 and 17? One hypothesis is predator satiation. By emerging in enormous numbers all at once, cicadas overwhelm predators. Birds, mammals, and other animals can't possibly eat them all, so most cicadas survive to reproduce. The long intervals between emergences mean predator populations can't specialize on cicadas. There's not enough food frequently enough to sustain a predator that relies primarily on cicadas. The prime number cycles may help avoid synchronizing with predators or parasites that have their own multi-year cycles. If a predator had a 2-year or 3-year cycle, and cicadas emerged every 12 years, they'd frequently coincide. But a 17-year cycle minimizes overlap with most shorter cycles. This is speculative, but it's an elegant explanation that connects number theory with evolutionary ecology. How cicadas count the years underground remains mysterious. They're tracking time in darkness, with minimal seasonal cues. Temperature might be involved, Nymphs could count seasonal cycles of soil warming and cooling. Developmental stages might be genetically programmed to take a specific number of years. But the precision is remarkable. Entire populations synchronized within days across large geographic areas. The evolution of social behavior in insects presents its own puzzles. Eusociality, the highest level of social organization, appears in bees, ants, wasps, and termites. In eusocial species, most individuals don't reproduce. Instead, they work to help a queen reproduce, caring for her offspring, foraging, building, and defending the nest. This seems to violate the fundamental principle of evolution. Individuals should maximize their own reproductive success. The explanation involves kin selection. In species like honeybees and ants, which have a haplodiploid sex determination system, sisters share more genes with each other than they would with their own offspring. A female honeybee shares 75% of her genes with her sisters, but only 50% with her daughters. So, genetically, she's better off helping her mother, the queen, produce more sisters than she would be producing her own offspring. But this explanation, while elegant, doesn't fully account for the evolution of eusociality. Termites are diploid, so the haplodiploid explanation doesn't apply to them. Some eusocial species, like naked mole rats, are also diploid. There must be other factors, ecological conditions that make cooperation advantageous, genetic predispositions towards staying in the nest rather than dispersing, the benefits of division of labor and collective defense. The puzzle deepens when we consider that eusociality has evolved independently multiple times, at least 12 times in insects alone. This suggests there are certain ecological and genetic conditions that repeatedly favor the evolution of extreme cooperation. But identifying exactly what those conditions are, and why they don't lead to eusociality, more often remains an active area of research. Spiders, solitary by nature, have their own collective mystery. Many spider species disperse by ballooning, climbing to a high point, releasing strands of silk into the air, and floating away on the wind. Young spiders can travel hundreds of miles this way, crossing oceans, colonizing remote islands. Charles Darwin observed spiders ballooning onto the Beagle far from shore, and marveled at the phenomenon. For a long time, scientists assumed ballooning spiders were simply carried by wind. But observations showed spiders can balloon even on calm days with no wind, and they seem to take off and land with some degree of control. Recent research suggests spiders might be using electric fields. Earth's atmosphere has a natural electric field, with the ground negatively charged and the upper atmosphere positively charged. This creates a potential gradient, typically around 100 volts per meter near the surface. Spider silk can carry an electric charge, and when spiders release silk into the air, the charged strands might be repelled by the ground's negative charge, lifting the spider upward. Experiments have shown that spiders can detect electric fields and respond to them, and that artificial electric fields can induce ballooning behavior even in the absence of wind. This would explain how spiders can control their takeoff and landing, sensing the electric field and adjusting the amount of silk they release. If true, this means spiders have been using atmospheric electricity for transportation for millions of years, exploiting a feature of Earth's environment that humans only began to understand recently. It's another example of organisms detecting and responding to aspects of their environment that we barely notice. Finally, a mystery that has practical consequences: colony collapse disorder in honeybees. Starting around 2006, beekeepers began reporting massive losses of honeybee colonies. The bees would simply disappear. Hives that had been strong and healthy would suddenly be empty, with only the queen and a few workers remaining, surrounded by ample food stores and developing brood. The missing bees were never found. They didn't return, and their bodies weren't discovered near the hives. Colony collapse disorder, or CCD, caused alarm because honeybees are crucial pollinators for many crops. About 1/3 of the human food supply depends on pollinators, and honeybees are the most important managed pollinators. Losses of 30 to 90% of hives were reported in some regions, threatening agricultural productivity. Researchers scrambled to identify the cause. Many factors were investigated: pesticides, particularly neonicotinoids that affect insect nervous systems, parasites like the varroa mite, pathogens including viruses and fungi, poor nutrition from monotonous diets in agricultural landscapes, stress from being transported long distances for pollination services, and combinations of these factors. The consensus that emerged is that CCD has no single cause. It appears to result from multiple stressors acting in combination. Bees weakened by poor nutrition are more susceptible to parasites. Parasites compromise immune systems, making bees more vulnerable to pathogens. Pesticide exposure impairs navigation and learning, making it harder for bees to return to the hive. Cold or wet weather adds additional stress. When enough stressors combine, colonies collapse. But why do the bees leave and never return? Sick bees normally don't abandon the hive. They die inside or just outside the entrance. The disappearance of workers suggests disorientation, perhaps from pesticides or pathogens affecting their nervous systems, causing them to get lost during foraging flights. Or it might be an adaptive behavior: sick bees leaving the hive to die elsewhere to avoid spreading disease to their nest mates. Colony collapse disorder has decreased in severity since its peak, possibly due to changes in pesticide use, improved parasite management, and better beekeeping practices. But bee populations remain under stress, and the phenomenon highlighted how little we understand about the complex interactions between managed insects, agricultural practices, environmental factors, and disease. Bees are among the most studied insects, kept by humans for thousands of years. Yet their collective behavior and health remain vulnerable in ways we're still working to comprehend. These mysteries of collective behavior, from the geometry of honeycombs to the disappearance of bees, remind us that intelligence is not always individual. Minds are not always required for mind-like behavior. Patterns can emerge from simple rules and local interactions, creating structures and behaviors that seem planned but arise spontaneously. The algorithm's nature has evolved. The solutions to navigation, optimization, coordination, and survival often work through principles we're only beginning to understand: decentralized, adaptive, robust, elegant in their simplicity, and powerful in their outcomes. As you drift towards sleep, imagine yourself as part of a collective, your thoughts like individual ants or bees, each following simple impulses, but together creating the pattern of consciousness, the sense of a unified self. Perhaps your mind is less a single thing than an emergent property, a colony of neurons firing in coordination, creating from their simple signals the rich experience of being human. Let that thought dissolve the boundaries between self and world, between individual and collective. You are one and many, a pattern that exists because countless small things work together, each doing its part without knowing the whole, creating something greater than themselves, creating you. We arrive now at the deepest mystery available to us, the one we carry inside our own skulls. The human brain, 3 pounds of tissue containing roughly 86 billion neurons, each connected to thousands of others, creating a network more complex than anything else we know in the universe. From this biological machinery emerges something that seems impossible: inner experience, the feeling of being someone, the sensation of existing. We call it consciousness, and despite centuries of philosophy and decades of neuroscience, we still don't truly understand what it is or how it arises. Consciousness is the hard problem. We can explain, at least in principle, how the brain processes information, how neurons fire in response to stimuli, how different regions coordinate to produce behavior. These are the easy problems of neuroscience, difficult in practice, but straightforward in concept. The hard problem is explaining why there's something it's like to be you. Why does seeing red feel like something? Why does pain hurt? Why is there an inner experience at all? You are conscious right now, aware of these words, perhaps aware of sounds around you, sensations in your body, thoughts drifting through your mind. This awareness, this subjective experience, is the most immediate and undeniable fact of your existence. Yet it's also the most difficult to explain scientifically. Consciousness doesn't seem to fit into the physical world as we understand it. Physics describes matter and energy, forces and fields, particles and waves. Nowhere in these equations is there a term for what it feels like to experience things. Some philosophers argue that consciousness is an illusion, that there's no actual inner experience, just complex information processing that tricks us into believing we have subjective awareness. But this seems to deny the most obvious fact about existence. Others suggest consciousness is fundamental, as basic to the universe as space and time, a property that emerges when information is integrated in certain ways. This is the integrated information theory, which proposes that consciousness arises from systems that process information in highly interconnected ways, creating a unified experience from many separate inputs. Another approach, global workspace theory, suggests consciousness is what happens when information becomes globally available to different brain systems. Most brain processing is unconscious, specialized modules handling vision, language, memory, motor control without awareness. But when information is broadcast to many systems at once, entered into the global workspace, we become conscious of it. Consciousness is the brain talking to itself, sharing information across regions so they can coordinate. But these theories describe correlates of consciousness, patterns of brain activity that accompany awareness. They don't explain why those patterns feel like something, why there's an experiencer experiencing. The explanatory gap remains. We can map consciousness to brain activity with increasing precision, showing which neurons fire when you see red or feel pain or think about tomorrow. But we can't explain the leap from neurons firing to the feeling of seeing red. Perhaps the question itself is flawed, based on assumptions about the relationship between mind and matter that don't hold. Perhaps consciousness isn't produced by the brain, but is an intrinsic aspect of certain physical systems. Perhaps it's not a thing at all, but a process, an ongoing construction that exists only in its own unfolding. We speak of consciousness as though it's a single phenomenon, but it might be many things: wakefulness, attention, self-awareness, sensory experience, each arising through different mechanisms. Every night, consciousness transforms. As you fall asleep, awareness fades, and for hours, you exist in altered states. Sometimes you dream, experiencing vivid narratives and sensations that seem real while they're happening. Sometimes you sink into deep sleep, a state so different from waking that it's like a small death, a temporary cessation of the self. Why do we dream? This question has puzzled humans throughout history. Ancient cultures saw dreams as messages from gods or journeys to other realms. Freud believed dreams were wish fulfillment, disguised expressions of unconscious desires. Modern neuroscience has provided insight into when and how dreaming occurs, but hasn't fully explained its function. Dreams happen primarily during REM sleep, rapid eye movement sleep, when the brain is highly active, but the body is paralyzed. During REM, the visual cortex activates, creating imagery. The limbic system, involved in emotions, becomes active while the prefrontal cortex, responsible for logical thinking and reality testing, quiets down. This explains why dreams are visually vivid and emotionally intense, but often illogical and bizarre. But why does the brain do this? Several theories exist. One is memory consolidation. During sleep, the brain replays experiences from the day, strengthening important memories and pruning unimportant ones. Dreams might be the subjective experience of this process, a story the conscious mind constructs from fragments of memories being sorted and stored. Studies show that people learning new skills show improvement after sleeping, particularly after periods of REM sleep. Another theory is emotional regulation. Dreams often involve scenarios that are threatening or emotionally charged. By experiencing these situations in the safe context of sleep, the brain might be processing emotions, working through anxieties and fears, learning to respond to challenges. People deprived of REM sleep show increased emotional reactivity and difficulty regulating mood. A third idea is that dreams serve no function at all. They're simply the brain's attempt to make sense of random neural activity during sleep. The activation synthesis hypothesis proposes that the sleeping brain generates noise, and the conscious mind, evolved to find patterns and construct narratives, weaves this noise into dream stories. Dreams are meaning imposed on meaninglessness, a side effect of having a pattern-seeking brain that never fully shuts down. Yet dreams feel meaningful. They can be sources of creativity and insight. Many artists, scientists, and inventors have reported solutions appearing in dreams. The surreal logic of dreams allows connections that waking thought might miss. Perhaps dreams are the mind playing, exploring possibilities without the constraints of reality, maintaining cognitive flexibility. We may never fully understand dreams because they're fundamentally private. You can describe your dreams, but no one else can experience them. Dream content varies enormously across individuals and cultures. Some people dream in color, others in black and white. Some have recurring dreams, others remember nothing. The subjective nature of dreaming makes it difficult to study objectively. Another reminder that consciousness in all its forms remains partly beyond science's reach. The mind's ability to influence the body is demonstrated powerfully by the placebo effect. Give someone a sugar pill and tell them it's a powerful painkiller, and many people will report reduced pain. Give them a saline injection and tell them it's chemotherapy, and some will lose their hair. The placebo effect is real, measurable, and powerful, yet it seems impossible. How can belief change biology? Placebos work through several mechanisms. In pain relief, the expectation of relief triggers the brain's endogenous opioid system, releasing natural painkillers. Brain imaging shows that when people take placebos believing they're receiving pain medication, their brains show activity in pain-modulating regions, actually changing how pain signals are processed. The pain doesn't disappear, but the brain's interpretation of those signals changes. Conditioning also plays a role. If you've experienced relief from a particular pill before, taking that pill again will trigger a conditioned response, even if the pill contains no active ingredient. Your body has learned to associate the pill with relief and begins physiological changes in anticipation. This is classical conditioning, the same process Pavlov demonstrated with dogs salivating to bells. But the placebo effect goes beyond pain. Placebos can affect heart rate, blood pressure, immune function, even the progression of some diseases. In Parkinson's disease, placebos can increase dopamine release in the brain, temporarily improving symptoms. In depression, placebos are nearly as effective as antidepressants in many studies, suggesting that much of antidepressant efficacy comes from expectation and the therapeutic context rather than the drug's chemical action. There's even a nocebo effect, where negative expectations cause harm. Tell people a harmless substance might cause headaches, and some will develop headaches. Warn of side effects, and people are more likely to experience them. The mind's power over the body is bidirectional, capable of healing and harming through belief alone. This raises profound questions. If belief can activate healing mechanisms, why don't we heal spontaneously? Why does deception seem necessary? The pill or injection tricking the mind into activating systems it apparently controls. Perhaps consciousness doesn't have direct access to these systems. Evolution built many of our healing and regulatory mechanisms to operate automatically, below awareness. The placebo effect might work by engaging conscious expectation and attention, which then indirectly influence unconscious processes. Understanding placebos better could revolutionize medicine. If we could activate healing mechanisms directly, without deception, we might treat many conditions more effectively with fewer side effects. But ethically, using placebos is complicated. Deception conflicts with informed consent. Yet telling someone they're receiving a placebo sometimes works anyway, suggesting the ritual of treatment, the attention and care, matters as much as the belief in a specific mechanism. The brain constructs your reality, and sometimes that construction glitches in revealing ways. Most people have experienced déjà vu, the eerie feeling that you've experienced the current moment before, that you're reliving something that already happened. You walk into a room and suddenly feel you've been there before, had this exact conversation, seen these exact people in these exact positions. The feeling is fleeting but intense, accompanied by a sense of strangeness, a brief rupture in normal experience. Déjà vu remains poorly understood. One theory is that it's a memory error. The brain is constantly recording experiences, and normally there's a clear distinction between perceiving and remembering. But sometimes the wires cross. A new experience gets tagged as a memory while it's still happening, creating the sensation that you're remembering something you're actually perceiving for the first time. Another explanation involves dual processing. The brain processes information through multiple pathways, usually synchronized. But if one pathway is delayed slightly, you might perceive something consciously. Then a fraction of a second later, a second pathway delivers the same information. Your brain interprets this as two separate events, the second one feeling like a memory of the first. Temporal lobe epilepsy can cause frequent déjà vu, suggesting the phenomenon involves the hippocampus and surrounding regions responsible for memory formation. Stimulating these areas electrically during brain surgery sometimes produces déjà vu. The experience might result from brief, minor epileptic-like activity, tiny misfirings that most people experience occasionally without it being pathological. Rarer is jamais vu, the opposite experience. Something familiar suddenly feels strange and unfamiliar. You look at a word you've written hundreds of times, and suddenly it looks wrong, like a foreign word, meaningless shapes. You enter your own home and momentarily don't recognize it. The sense of familiarity that usually accompanies well-known things disappears, leaving only the raw perception without its emotional and contextual associations. Jamais vu can occur in temporal lobe epilepsy, in migraine auras, or simply from repetition. Say a word over and over, and it begins to sound strange, losing its meaning. This is semantic satiation, a form of jamais vu induced by overexposure. The neural circuits that encode familiarity and meaning temporarily exhaust themselves, leaving the perception stripped of its usual context. Even stranger is presque vu, literally almost seen. The feeling that you're on the verge of an insight or memory that never quite arrives. It's the tip of the tongue phenomenon extended beyond words, a sense that understanding is imminent, but remains tantalizingly out of reach. You feel you're about to grasp something important, a connection or realization, and it hovers just beyond consciousness, then fades. Some researchers consider presque vu related to creativity, moments when the unconscious mind is working on problems the conscious mind can't yet access. These experiences reveal how much of perception is construction. You don't passively receive reality. Your brain actively builds your experience from sensory data, memories, predictions, and emotional states. Most of the time, this construction is seamless, creating a stable sense of a continuous world. But glitches happen, moments when the construction becomes visible, when you glimpse the scaffolding behind experience. Choice blindness demonstrates another unsettling truth about consciousness. In experiments, people are shown two photographs of faces and asked to choose which one they find more attractive. After choosing, they're given the photograph to look at more closely and asked to explain their choice. But through sleight of hand, experimenters sometimes switch the photographs, giving participants the photo they didn't choose. Remarkably, most people don't notice. They look at the face they rejected and explain why they chose it, confabulating reasons for a choice they never made. This happens not just with faces, but with preferences for jam, political opinions, moral judgments. People fail to notice when their choices are switched and confidently explain decisions they didn't make. This suggests that our access to our own decision-making processes is limited. We don't actually know why we make many choices. Instead, we observe our own behavior and infer reasons, constructing explanations after the fact. This is disturbing because we feel certain about our choices and reasons. Subjectively, it seems you know why you prefer one thing over another. But choice blindness experiments show this is often an illusion. Your conscious mind doesn't have privileged access to decision-making. It receives outputs from unconscious processes and then rationalizes them, creating a coherent narrative that may have little to do with actual causes. The rubber hand illusion reveals similar flexibility in how the brain constructs bodily awareness. Sit at a table with your left hand hidden and a rubber hand visible in front of you. An experimenter strokes both your hidden real hand and the visible rubber hand simultaneously. After a minute or so, most people begin to feel the stroking sensations coming from the rubber hand. They feel ownership of the fake hand. When the experimenter suddenly hits the rubber hand with a hammer, people flinch and feel a jolt of fear, as though their real hand were threatened. The brain integrates visual and tactile information to determine what's part of your body. When these signals align, even for an obviously fake hand, the brain incorporates the fake hand into your body image. This shows that bodily self-awareness, the sense of where your body is and what's part of it, is surprisingly fluid, constantly updated based on sensory inputs. This has implications for phantom limbs, the sensations amputees often feel from missing body parts. It relates to out-of-body experiences, which might occur when the brain's integration of sensory signals is disrupted. It's being explored for prosthetics, helping amputees incorporate artificial limbs more fully into their body schema. The boundary between self and not self, which seems so fundamental, is actually a construction, flexible and revisable. Even sleep, which seems universal among animals, has strange variations. Many marine mammals and some birds exhibit unilateral sleep, where half the brain sleeps while the other half remains awake. Dolphins, seals, and whales do this to continue swimming and surfacing to breathe. If they slept completely, they might drown. So one hemisphere enters slow-wave sleep while the other maintains basic vigilance and motor control. Birds do this during long migratory flights. Alpine swifts can stay airborne for months, sleeping on the wing with half their brain at a time. Frigate birds soar over oceans for weeks, catching brief moments of unilateral sleep while riding air currents. This allows them to rest without stopping, sleeping while flying. The mechanism involves remarkable neural coordination. The two hemispheres must operate semi-independently, one producing sleep waves while the other maintains wakefulness. The eye connected to the sleeping hemisphere often closes while the other stays open. Motor control must be maintained smoothly despite asymmetric brain states. Humans don't typically exhibit unilateral sleep, but there's a phenomenon called the first night effect. When sleeping in an unfamiliar place, one hemisphere shows less deep sleep than the other, maintaining higher vigilance. This might be a vestige of a more general ability our ancestors had, sleeping with one eye open in potentially dangerous environments. These glimpses into consciousness, dreams, perception, and the body's boundaries remind us that the mind is stranger than it appears from inside. We experience the world as though we're passive observers receiving information, making free choices, knowing ourselves. But beneath this smooth surface lies a churning complexity of processes, most of them unconscious, constructing reality moment by moment from fragments and predictions, telling us stories about ourselves that may not be true, maintaining the illusion of a unified self when we might be more like communities, multiple processes operating simultaneously, their outputs integrated into something that feels singular, but may not be. As you release yourself to sleep now, let go of the illusion of control. Your conscious mind doesn't need to manage breathing or heartbeat, doesn't need to direct dreams or organize memories. Those processes will continue without your attention, without your awareness. You are both subject and object, both the observer and the observed, both the storyteller and the story. Let yourself dissolve into that paradox. Let consciousness fade as it does every night, trusting in the resilience of whatever you are beneath awareness, the biological machinery that sustains you, the mystery that wakes again tomorrow, reassembled, continuous with today, yet subtly different, forever changing yet somehow still you. We descend now into the deepest questions, to the edge where physics meets philosophy, where mathematics confronts impossibility. These are mysteries about the nature of reality itself, about what it means for something to exist, about whether there are limits to what we can know. Here, in the realm of quantum mechanics and fundamental forces, the universe reveals behaviors so strange that they challenge our most basic intuitions about how things should be. Consider a simple quantum system, a particle that exists in a superposition of states, neither here nor there, but somehow both until you measure it. Quantum mechanics tells us that measurement collapses the superposition, forcing the particle into one definite state. But here's something strange. If you measure the particle repeatedly, very rapidly, the superposition never evolves. The particle becomes frozen, locked in its initial state by the very act of observation. This is the quantum Zeno effect, named after the ancient Greek philosopher Zeno, who proposed paradoxes about motion and change. In his most famous paradox, an arrow in flight is motionless at every instant. So how can it ever move? The quantum Zeno effect is a real physical manifestation of this idea. Continuous observation prevents change. A watched quantum pot never boils. The effect has been demonstrated experimentally. Quantum systems that would normally decay or transition between states can be stabilized by frequent measurements. The mechanism involves the collapse of the wave function. Each measurement resets the system, and if measurements happen faster than the system's natural evolution time, the system never gets a chance to change. This raises profound questions about the relationship between observation and reality. In classical physics, observing something doesn't change it fundamentally. You can watch a planet orbit the sun without affecting its motion. But in quantum mechanics, observation is not passive. It's an interaction that fundamentally alters the system. The quantum Zeno effect is an extreme demonstration of this. Reality depends on whether and how often you look at it. But what counts as observation? Does it require consciousness, a human observer? This question lies at the heart of the Wigner's friend paradox, a thought experiment that extends Schrödinger's famous cat scenario. Imagine a friend inside a laboratory performing a quantum measurement. From outside the lab, you can treat the entire laboratory, including your friend and the measurement apparatus, as a quantum system in superposition. But from inside the lab, your friend has performed a measurement and obtained a definite result. Who's right? Has the wave function collapsed, as your friend believes, or is the entire laboratory still in superposition, as the mathematics suggests from your external perspective? The paradox reveals a tension in quantum mechanics about the nature of observation and the boundary between quantum and classical reality. Some interpretations resolve this by proposing that wave functions never collapse. Instead, the universe branches into multiple realities, one for each possible outcome. Your friend sees one result in their branch, while other versions of your friend in other branches see different results. This is the many worlds interpretation, which sounds like science fiction, but is taken seriously by many physicists because it's mathematically consistent and doesn't require adding special collapse mechanisms to the theory. Another approach is quantum Darwinism, which explains why we experience a classical world despite living in a quantum universe. The idea is that quantum information gets amplified and distributed into the environment. When a quantum system interacts with its surroundings, it leaves multiple imprints, copies of certain information in many environmental degrees of freedom. These redundant copies are what we can measure and agree upon, creating objective classical reality from quantum substrate. Only certain information gets amplified in this way, the information that's stable under environmental interaction. This explains why we see definite positions and states rather than superpositions. The environment acts as a witness, constantly measuring quantum systems, and through this natural selection process, certain classical properties emerge as the most robust and observable. Reality is not purely objective or subjective, but intersubjective, constructed through the redundancy of information in the environment. These quantum mysteries connect to deeper problems in physics and mathematics. Consider three celestial bodies, 3 planets or stars, attracting each other through gravity. Predicting their future positions might seem straightforward. We have Newton's laws, elegant equations describing gravitational attraction. For 2 bodies, the math is simple, producing regular elliptical orbits. But add a third body, and the problem becomes extraordinarily difficult. The three-body problem has no general analytical solution. You cannot write down equations that predict the positions of three mutually attracting bodies at any future time. The system is chaotic in the technical sense. Tiny differences in initial conditions lead to dramatically different outcomes. Two configurations that start almost identically will diverge exponentially over time, their futures becoming completely different. This doesn't mean three-body systems are random. They follow deterministic laws. But determinism doesn't guarantee predictability. Chaos means that to predict the distant future precisely, you'd need to know the initial conditions with infinite precision, which is impossible. There's a fundamental limit to prediction built into the mathematics, even though the underlying physics is perfectly well defined. Chaos appears throughout nature, in weather systems, which is why long-term weather prediction is impossible, in fluid turbulence, which we encountered earlier, in population dynamics, asteroid orbits, heart rhythms, stock markets. The universe is full of systems that are deterministic yet unpredictable, orderly yet chaotic. The three-body problem was the first recognition of this deep feature of nature, discovered in the late 19th century, and still not fully understood today. Related to turbulence is another unsolved problem we touched on earlier: the Navier-Stokes equations. These equations describe fluid flow, from water in a pipe to air over a wing to plasma in stars. They're fundamental to engineering and meteorology, used constantly in practical calculations. Yet we cannot prove that smooth solutions to these equations always exist. For certain initial conditions, solutions might develop singularities, points where velocity or other quantities become infinite in finite time. If such singularities exist, the equations break down, ceasing to describe physical reality. We don't know whether they can occur. This is one of the Millennium Prize problems, with $1 million reward for a proof either that smooth solutions always exist or for a counterexample showing they sometimes don't. The difficulty connects to turbulence and the cascade of energy across scales. As turbulent eddies break into smaller eddies, energy transfers to increasingly fine scales. The question is whether this cascade can become so extreme that mathematical singularities form. Physically, we know fluids are made of molecules, so there's a smaller scale where fluid equations no longer apply. But mathematically, treating fluids as continuous media, the question remains open. Another Millennium Prize problem concerns the Yang-Mills theory and the mass gap. Yang-Mills theories describe fundamental forces in nature through quantum field theory. The strong nuclear force, which binds quarks together inside protons and neutrons, is described by a Yang-Mills theory. Experiments show that particles in these theories have mass. There's a mass gap, a minimum energy required to create particles. But proving this mathematically has been impossible. The equations of Yang-Mills theory are known, but rigorously deriving the existence of a mass gap from those equations exceeds current mathematical techniques. The problem involves understanding how quantum field theories behave at all energy scales, from the highest energies where particles behave almost freely to low energies where they bind together into composite particles. This isn't just mathematical abstraction. The mass gap is crucial to understanding protons, neutrons, and atomic nuclei. Most of the mass of ordinary matter doesn't come from the masses of individual quarks, which are tiny, but from the energy of the strong force field binding quarks together. This energy, divided by the speed of light squared, manifests as mass through Einstein's equation. Understanding this mathematically would deepen our grasp of where matter's mass comes from. High-temperature superconductivity presents a different kind of mystery. Superconductivity, the phenomenon where materials conduct electricity with zero resistance, was discovered in 1911. For decades, it required temperatures near absolute zero, impractical for most applications. Then in 1986, scientists discovered ceramic materials that superconduct at much higher temperatures, above the boiling point of liquid nitrogen. This was unexpected. The standard theory of superconductivity, developed in the 1950s, explains conventional superconductors beautifully. Electrons pair up through interactions mediated by vibrations in the crystal lattice, and these pairs can flow without resistance. But the theory predicts this mechanism should stop working at higher temperatures. The ceramic high-temperature superconductors shouldn't exist according to conventional theory, yet they do. More than 35 years later, we still don't fully understand how high-temperature superconductors work. The materials are complex, often containing layers of copper oxide with unusual electronic properties. Various mechanisms have been proposed involving quantum effects, magnetic interactions, or exotic pairing mechanisms, but no consensus has emerged. This is frustrating because understanding the mechanism might allow us to design materials that superconduct at room temperature, which would revolutionize technology, enabling lossless power transmission, faster computers, and more efficient motors. The strong nuclear force holds more mysteries. Quarks, the particles that make up protons and neutrons, are bound by gluons, particles that carry the strong force. In principle, gluons should be able to bind to each other, forming particles called glue balls, made entirely of gluons with no quarks. Theory predicts glue balls should exist, and even specifies their properties, but definitively detecting them in experiments has been elusive. The difficulty is that glue balls would have similar masses and decay patterns to conventional particles made of quarks, making them hard to distinguish. Some experimental results hint at glue ball candidates, but confirming their identity requires more precise measurements. Finding glue balls would be important confirmation of quantum chromodynamics, our theory of the strong force, demonstrating that force carriers themselves can form bound states. Protons are stable. You're made of protons, and they don't decay, which is fortunate for your continued existence. But some theories in particle physics predict that protons should eventually decay, just on timescales much longer than the current age of the universe. Grand unified theories, which attempt to unify the electromagnetic, weak, and strong forces, often predict proton decay with lifetimes around 10 to the 33 years or longer. Experiments have searched for proton decay by monitoring enormous volumes of water or other materials, watching for the telltale signatures of a proton transforming into lighter particles. So far, nothing has been observed, setting lower limits on the proton lifetime of over 10 to the 34 years. This is a trillion times longer than the age of the universe. The experiments are watching trillions of protons, hoping to catch one decaying, but the universe isn't cooperating. If protons never decay, certain theoretical frameworks are wrong. If they do decay, but with even longer lifetimes than we can currently probe, we might never know. It's possible that one of the most basic facts about matter, whether it's ultimately stable or just extraordinarily long-lived, will remain uncertain indefinitely. The decay of particles called kaons revealed another deep mystery. Kaons can transform into their antiparticles and back again through quantum oscillations. In 1964, experiments showed that this oscillation violates a symmetry called CP symmetry, which relates particles to their mirror images combined with swapping particles and antiparticles. This CP violation was unexpected and remains not fully explained. CP violation is connected to the baryon asymmetry we discussed earlier, the fact that the universe contains more matter than antimatter. If CP symmetry were perfect, the Big Bang should have created equal amounts of matter and antimatter, which would have annihilated, leaving only light. The small CP violation observed in kaon decays provides a mechanism for generating matter-antimatter asymmetry, but the amount is too small to explain the universe we see. There must be additional sources of CP violation, possibly in neutrino oscillations or in physics beyond the standard model. Experiments are searching for these additional sources, trying to understand why the universe chose matter over antimatter. It's one of the most fundamental questions in cosmology, and the answer involves subtle details of how particles decay, connecting the smallest scales to the largest. The cosmic lithium problem takes us back to the first minutes after the Big Bang. During nuclear synthesis, in the first few minutes of the universe's existence, protons and neutrons combine to form the lightest elements: hydrogen, helium, and trace amounts of lithium and beryllium. We can calculate how much of each element should have been produced based on the conditions at that time. For hydrogen and helium, observations match predictions beautifully. But lithium is problematic. The oldest stars in the universe, which preserve the primordial abundances most faithfully, contain only about a third as much lithium-7 as theory predicts. This is the cosmic lithium problem. Either our calculations are wrong, or something destroyed lithium in the early universe or in stars, or the observations are systematically off. Various solutions have been proposed. Perhaps lithium-7 was destroyed in stars more efficiently than we thought, settling below the surface where we can't see it. Perhaps there were additional particles in the early universe, like sterile neutrinos or dark matter particles, that affected nucleosynthesis. Perhaps our understanding of nuclear reaction rates is slightly off. But none of these explanations is entirely satisfactory. The lithium problem remains a small but persistent discrepancy between theory and observation, a hint that something about the early universe or stellar evolution is not quite right in our models. Finally, a contemporary mystery closer to home. In 2020, scientists announced the detection of phosphine in Venus's atmosphere. Phosphine is a gas associated with biological activity on Earth, produced by microbes in oxygen-poor environments. Finding it on Venus was unexpected. Venus's surface is hot enough to melt lead. Its atmosphere is mostly carbon dioxide with clouds of sulfuric acid, and conditions are utterly hostile to life as we know it. Yet the spectroscopic signatures suggested phosphine was present at high altitudes in the atmosphere. If confirmed, this demanded explanation. Could there be microbial life floating in Venus's clouds, in a temperate zone where conditions are less extreme? Or could phosphine be produced by unknown geological or chemical processes? The detection sparked controversy. Other scientists reanalyzed the data and questioned whether phosphine was really detected, or if the signals could be explained by other molecules like sulfur dioxide. New observations with different telescopes have produced conflicting results. As of now, the Venus phosphine mystery remains unresolved. We don't know if phosphine is really there, and if it is, we don't know what's producing it. This uncertainty reminds us that even with sophisticated instruments and techniques, observations can be ambiguous, interpretations uncertain. Science progresses through debate and further observation, and not all mysteries resolve quickly. Some linger for decades or centuries, waiting for better technology or new insights. The universe is under no obligation to reveal its secrets on our timeline. These mysteries, from quantum paradoxes to missing lithium to enigmatic gases on Venus, share a common theme: the limits of knowledge. Some limits are practical, waiting for better instruments or computers. Others are fundamental, built into the mathematics or the nature of observation itself. Chaos means we cannot predict everything even when we know the laws. Quantum mechanics means reality itself might depend on how we look at it. Mathematics contains problems we cannot solve, questions we cannot answer. There is strange comfort in this. The universe remains mysterious not because we're ignorant, though we are, but because mystery is woven into the fabric of existence. Uncertainty is not a bug, but a feature. The future is open, not because we lack information, but because information has limits. Reality is participatory, not because we're special, but because observation and existence are entangled at the deepest level. As you sink towards sleep, let go of the need to understand. Let go of the illusion that the world is fully knowable, that mysteries are just puzzles awaiting solution. Some questions have no answers. Some paradoxes are real. Some limits cannot be crossed. And this is not failure, but the way things are, the universe revealing its nature as fundamentally, beautifully, irreducibly mysterious. Rest in that mystery. Let it hold you as you release your grip on consciousness, as you descend into dreams, as you dissolve once more into the unknowable depths from which you emerged and to which you return each night. That darkness which is not emptiness but fullness beyond comprehension, the ground of all being, forever hidden, forever present, forever calling you home. We arrive now at the end of our journey, to questions that blur the boundaries between science and wonder, between what we can measure and what we can only contemplate. These final mysteries are softer, more philosophical, asking not just what we don't know, but what it means to exist in a universe where so much remains unknown. They invite us to look outward at the cosmos and inward at ourselves, to consider how fragile and improbable our presence here truly is. Our Earth orbits the Sun at precisely the right distance for liquid water to exist on its surface. This is the Goldilocks zone, not too hot, not too cold, but just right for life as we know it. Yet the boundaries of this zone are surprisingly uncertain. Venus, only slightly closer to the Sun, is a hellscape. Mars, only slightly farther, is frozen and desiccated. The margin for habitability seems narrow, yet we don't know exactly how narrow. Different models produce different estimates for where the Goldilocks zone begins and ends. The boundaries depend on atmospheric composition, cloud cover, greenhouse effects, planetary rotation, and countless other factors. Some models suggest Earth sits comfortably in the middle of the zone. Others place us near the inner edge, implying we're precariously close to a runaway greenhouse effect like Venus experienced. This uncertainty matters for understanding how common habitable planets might be. If Goldilocks zones are wide, many planets could support life. If they're narrow, habitable worlds might be rare. We're searching for life on exoplanets, planets orbiting other stars, and deciding where to look depends on understanding habitability. Yet even in our own solar system, with just one sun and a handful of planets to study, we cannot precisely define the boundaries of the zone that made us possible. Perhaps the answer lies elsewhere in the solar system. Saturn's moon Enceladus is a small icy world, only about 500 kilometers across, its surface covered in bright white ice. It seems lifeless, frozen, far beyond any reasonable habitable zone. Yet beneath that ice lies an ocean of liquid water, kept warm by tidal heating as Saturn's gravity needs the moon's interior. We know this ocean exists because Enceladus sprays plumes of water vapor and ice crystals into space through cracks in its southern hemisphere. The Cassini spacecraft flew through these plumes, analyzing their composition, and found not just water but organic molecules, salts, and even hints of hydrothermal activity on the ocean floor. All the ingredients for life, as we understand it, are present in this dark subsurface ocean. Could life exist there? Microbes thriving around hydrothermal vents, never seeing sunlight, living on chemical energy from the moon's interior? We have no way to know without sending a mission to sample the ocean directly, perhaps by landing on Enceladus and drilling through the ice, or by flying through the plumes again with more sophisticated instruments. But the possibility haunts us. Life might exist not just in a narrow Goldilocks zone around stars, but anywhere liquid water and energy are found, hidden beneath ice, shielded from radiation, independent of sunlight. If life can exist in such places, the universe might be full of it, hidden in subsurface oceans of moons and dwarf planets, in caves deep underground on Mars, in places we haven't thought to look because they don't match our expectations. The question of whether we're alone becomes even more tangled. We might be surrounded by life, yet unable to detect it, separated by barriers of ice and distance. Looking outward into the cosmos, we find structures both vast and empty. In 2007, astronomers discovered an enormous void in the constellation Eridanus, a region of space nearly 1 billion light-years across that contains almost no galaxies. The cosmic microwave background, the afterglow of the Big Bang, appears slightly colder in this direction, suggesting a true absence of matter. Such voids exist elsewhere in the universe, but this one is unusually large. It's been called a supervoid, and its existence is difficult to explain. The early universe was remarkably uniform, with matter distributed almost evenly. Over billions of years, gravity amplified small differences, creating the cosmic web of galaxies, clusters, and filaments we see today. But this process should take longer than the current age of the universe to create voids as large as the one in Eridanus. Various explanations have been proposed. Perhaps the void is not as empty as it appears, containing dark matter and a few faint galaxies we haven't detected. Perhaps it's the imprint of something from before the Big Bang, a structure inherited from whatever existed beforehand. Perhaps it's evidence of physics beyond our current models. Or perhaps it's simply a statistical fluke, an unusually large but not impossible fluctuation in the distribution of matter. The hole in the galaxy is a reminder that the universe operates on scales we can barely conceive, that structures exist so vast they challenge our theories. It invites us to zoom back out, to remember that everything we know, all of human history, every story ever told, every person who has ever lived, exists in an infinitesimally small corner of a universe filled with such incomprehensible vastness. Back on Earth, in a patch of rainforest in Panama, a mystery unfolded quietly over decades. Barro Colorado Island is one of the most studied tropical forests in the world, monitored continuously since the 1920s. Ornithologists have tracked bird populations there for generations, creating detailed records of which species nest on the island, how many individuals, and how they change over time. In recent decades, researchers noticed something disturbing. Birds were disappearing, not just declining in number, but vanishing entirely from the island. Species that had been common residents were no longer found. Insectivorous birds, those that eat insects, were particularly affected. By the early 2000s, the forest was significantly quieter, its bird communities depleted in ways that didn't match patterns seen elsewhere. What caused this? Climate change might be involved, altering insect populations or forest structure. Fragmentation could play a role. Barro Colorado is an island created when the Panama Canal was built, isolating it from surrounding forest. But similar islands nearby didn't show the same pattern. Some researchers suggest cascading ecological effects, changes in one part of the ecosystem rippling through others in unpredictable ways. The mystery is compounded by uncertainty. Bird monitoring is difficult and expensive. Records have gaps. Changes might have started earlier than we noticed, or might not be as severe as they appear. The disappearance of Barro Colorado's birds is not a single mystery, but a web of interconnected questions about ecosystems, climate, and our ability to observe and understand complex natural systems in transition. It's a reminder that even well-studied places hold secrets, that ecosystems are more fragile and dynamic than we often realize. The bird's disappearance is not just a loss of biodiversity, but a loss of knowledge, a silencing of voices that once filled the forest, relationships between species that we never fully documented before they vanished. In the oceans, relationships are breaking down in real time. Coral reefs are built through symbiosis, partnerships between coral animals and microscopic algae, called zooxanthellae, that live inside coral tissues. The algae photosynthesize, producing sugars that feed the coral. The coral provides shelter and nutrients for the algae. This partnership has existed for millions of years, creating the most biodiverse ecosystems in the ocean. But warming waters stress this relationship. When corals are stressed by heat, they expel their algae, a process called bleaching. The coral turns white, revealing the calcium carbonate skeleton beneath. Without their algae, corals starve. If temperatures return to normal quickly, corals can recover, recruiting new algae. But if stress persists, corals die. Bleaching events are becoming more frequent and severe. The Great Barrier Reef has experienced multiple mass bleaching events in recent years. Reefs worldwide are in decline. We're witnessing the breakdown of ancient symbioses, partnerships that have sustained entire ecosystems, collapsing under the pressure of environmental change, happening faster than evolution can respond. What's mysterious is why some corals bleach while others in the same reef don't. Some individual corals, some species, seem more resilient. They maintain their symbionts or recover more quickly. Understanding this variation is crucial for conservation, for identifying which corals might survive and which reefs might persist as climate continues to change. But the mechanisms of resilience are complex, involving genetics, symbiont diversity, prior exposure to stress, and factors we probably haven't identified. Symbiosis creates other mysteries. Some ants live symbiotically with acacia trees. The trees provide hollow thorns where ants nest and produce nectar and protein-rich structures that ants eat. In return, ants defend the trees aggressively, attacking herbivores and even trimming surrounding vegetation to prevent other plants from shading their host tree. But different ant species protect the same tree species in different ways and with different levels of aggression. Some ant species are better defenders, attacking more effectively and keeping trees healthier. Trees inhabited by less aggressive ants grow more slowly and suffer more damage. Yet the less aggressive ants persist. Why don't the better defenders outcompete them? Research suggests there's a trade-off. Aggressive ants provide better defense, but also consume more of the tree's resources. From the tree's perspective, there's an optimal level of ant aggression. Too little, and the tree suffers from herbivores. Too much, and the tree suffers from its own defenders. Trees might have mechanisms to control which ant species colonize them, or ant competition might maintain a balance between aggressive and less aggressive species. This dynamic resembles warfare, with trees as contested territory and different ant colonies as competing armies. But it's also cooperation, with trees and ants locked in evolutionary arms races and alliances that shape both partners. Understanding these relationships requires thinking about ecosystems not as collections of species, but as networks of interactions, evolutionary conflicts and collaborations playing out across generations. In the deep ocean, worms construct homes with architectural precision that rivals anything insects build. Chaetopterid worms, sometimes called goblet worms, live in U-shaped tubes buried in sediment. The worms secrete mucus that hardens into parchment-like material, forming tubes that can be 30 centimeters long. The tubes have precise dimensions, smooth inner surfaces, and openings that align with the seafloor. What's remarkable is the consistency. Worms of the same species build virtually identical tubes, with the same dimensions and angles, even though each worm constructs its tube individually without templates or tools. How do they achieve this precision? The worms are soft-bodied with simple nervous systems, yet they produce structures with the regularity of manufactured objects. The mechanism likely involves the worm's body as a template, the tube diameter matching the worm's body size, and behaviors that ensure consistent tube shape. The worm rotates in the tube as it secretes material, creating smooth walls. It periodically reverses direction, perhaps creating structural features at regular intervals. But the details remain largely unstudied. Deep-sea organisms are difficult to observe, and goblet worms have not received much attention from researchers. Their precision reminds us that biological construction, at every scale, produces consistent results through mechanisms we often don't understand. The worm tube, the honeycomb, the nautilus shell, all emerge from simple repeated actions guided by genetics and physics, creating order without blueprints, architecture without architects. In 1997, something strange happened in Buga, Colombia. On November 16th, a luminous sphere was reported in the sky above the town. Multiple witnesses described a bright, spherical object hovering silently. Then the sphere exploded or transformed, fragmenting into multiple smaller lights that dispersed in different directions. Some witnesses reported a sound like thunder, though others heard nothing. The Buga sphere incident was investigated by local researchers and military officials, but never satisfactorily explained. No conventional aircraft or weather phenomena matched the descriptions. Skeptics suggested it might have been a bolide, a bright meteor, but the duration and behavior didn't match typical meteors. Others proposed more exotic explanations, though none were confirmed. What makes the incident notable is not that it happened. Unusual sightings occur regularly, and most are eventually explained, but that it remains genuinely ambiguous. Multiple credible witnesses observed something, but the observations don't cleanly fit any conventional explanation. It's a reminder that the sky holds surprises, that not every unexplained observation is evidence of aliens or the supernatural, but also that not everything gets explained. Some events remain anomalous, neither proof of anything extraordinary nor comfortably categorized as mundane. From the skies of Columbia, we turn to the laboratories of parapsychology, to experiments that probe the boundaries between science and the seemingly impossible. Precognition, the ability to perceive future events, violates everything we understand about causality and time. Yet experiments have repeatedly claimed to find evidence for it. The most prominent recent work comes from psychologist Daryl Baim, who in 2011 published studies claiming to show that people's responses to stimuli were influenced by future events. For example, participants seemed to perform better on memory tests for words they would be shown in the future, after the test, as though their future experience reached backward in time to help them in the present. These results are controversial. Critics point to statistical issues, small effect sizes, and the failure of many replication attempts. The scientific consensus remains that precognition is not real, that the experiments reflect subtle biases in methodology or analysis rather than actual time reverse causality. Yet the experiments persist, and some meta-analyses suggest small but consistent effects across many studies. Whether precognition is real is less interesting than what the debate reveals about science's boundaries. How do we handle claims that violate fundamental principles? Extraordinary claims require extraordinary evidence, but what counts as extraordinary depends on what we already believe. If precognition experiments show positive results, should we accept them and revise our understanding of time? Or should we assume methodological flaws must exist even if we can't identify them? Science proceeds through skepticism and openness, doubting claims until evidence becomes overwhelming, yet remaining willing to follow evidence even when it challenges core beliefs. The precognition debate highlights this tension. Most scientists believe the effects will eventually be explained away, but some maintain that the evidence, flawed though it may be, is worth investigating further. The question remains genuinely open, not because precognition is likely, but because definitively closing the question is harder than it might seem. All these mysteries, from Goldilocks zones to vanishing birds to precognition experiments, circle around a final, fundamental question. What is the nature of reality itself? This is not a scientific question in the usual sense, not something we can answer through experiments and observations alone, but a philosophical inquiry that science touches but cannot resolve. Is reality fundamentally physical, made of particles and fields following mathematical laws? Or is consciousness primary, and the physical world in some sense a construction of mind? Is there an objective reality independent of observers? Or does reality require observation to exist? Are we biological machines, our thoughts and feelings nothing but electrochemical processes? Or is there something more, some aspect of existence that transcends mechanism? Different philosophical traditions answer these questions differently. Materialism says everything is physical. Idealism says everything is mental. Dualism says both exist as separate substances. Panpsychism suggests consciousness is a fundamental property of matter, present in some form, even in simple systems. Quantum mechanics seems to suggest that observation plays a role in determining reality, but what observation means remains contested. Perhaps these questions have no answers, or perhaps the answers are not the kind we expect, not true or false, but more like lenses through which we view experience, each capturing some aspects while missing others. Perhaps the nature of reality is not something we can step outside and examine objectively because we're part of it, embedded in the thing we're trying to understand. Science has revealed that the universe is stranger than our ancestors could have imagined. Quantum superpositions, curved space-time, dark matter and energy, the expansion of space itself. Yet for all this strangeness, for all we've learned, the deepest questions remain. Why is there something rather than nothing? Why these laws of physics rather than others? Why does the universe seem comprehensible to us at all? We are pattern-seeking creatures in a universe full of patterns, minds that emerged from matter, trying to understand matter and mind. We build telescopes and microscopes, particle accelerators and space probes, extending our senses across scales from the infinitesimal to the cosmic. We develop mathematics and theories, languages for describing what we find. And everywhere we look, we find beauty and mystery intertwined, order and chaos, understanding and puzzlement. Perhaps the greatest mystery is not any particular unsolved problem, but the fact that mysteries persist at all, that despite centuries of investigation, the universe keeps revealing new depths. Every answer raises new questions. Every solved puzzle exposes more profound puzzles beneath. The boundary between known and unknown doesn't disappear as knowledge grows. It expands, revealing larger territories of ignorance surrounding each island of understanding. And so we return to where we began, floating in the darkness, surrounded by questions without answers, mysteries without solutions. We have traveled from the edge of the observable universe to the inner workings of cells, from the first moments after creation to the persistent puzzle of consciousness, from ancient monuments to vanishing birds, from quantum paradoxes to the breakdown of coral reefs. We have encountered 100 mysteries, 100 invitations to wonder, 100 reminders that reality is far stranger and more beautiful than we sometimes remember in the busyness of daily life. These mysteries are not obstacles to be overcome, but gifts to be cherished. They remind us that we live in a universe of infinite depth, that every answer leads to deeper questions, that the project of understanding is never complete. The scientist examining cosmic radiation, the bird watcher noting absences in the forest, the child asking why the sky is blue, all participate in the same ancient human endeavor. The attempt to make sense of existence, to find meaning in pattern, to transform mystery into understanding, while knowing that mystery will always remain. As you rest now, as consciousness fades and sleep takes you, carry with you this thought. You are a mystery contemplating mysteries, an improbable arrangement of atoms that has somehow become aware, capable of wonder, able to ask questions that may have no answers. The universe has organized itself in you, into something that can look back at itself and marvel. This is perhaps the deepest mystery of all, that matter can wake up, that the cosmos can know itself through your eyes, that existence can reflect upon its own nature. Let these mysteries be your companions in sleep and in waking. Let them remind you that you live in an age of exploration as profound as any in history, that unknowns surround you always, that wonder is not childish, but the appropriate response to a reality more strange and surprising than any fiction. The universe has kept its secrets for billions of years, and it keeps them still, patient and vast, waiting for minds brave enough to ask, humble enough to admit ignorance, and curious enough to keep searching, knowing that every discovery reveals how much remains unknown. Rest now in that beautiful uncertainty, in the comfort of mystery, in the knowledge that tomorrow the questions will still be there, eternal and unanswerable, and absolutely essential, calling you back to wonder, inviting you once more into the magnificent puzzle of existence itself. Good night, and have a great, relaxing sleep.